How much time do we have?
Forever.
We'll see how long I can stay.
Hey, everybody. This is This Week in Science, and we are going to record our podcast. If you're watching this right now, how exciting. How exciting for you. You're joining us. Welcome. Yes, this is the recording of the TWIS broadcast, of the podcast. But we're going to edit things, and that'll be the podcast. So what you're watching now, this is unedited, raw, unfiltered, live. You know, still we try and be family friendly, except for Justin occasionally get going on rants, getting emotional.
That was the first slip in. I feel like it's been years.
Very long time, years. It was good. Okay, but we're ready to go. Are we here? Do we sound good? Can you see us? Yes, people can see us. We're live.
Right.
Say a word.
Am I audible?
You're audible, Justin.
Yes. Hi, this is Justin. I am speaking.
You're speaking,
Right.
and
Ooh,
Blair.
your mouth even.
I like how you look like you got a little party hat going on in the background.
Right.
Right
Or a crown for a princess, you know.
Celebrating.
Princess crown.
I've always had this fantasy of doing the show with a pre-recording of me talking about a story, where I start using I start talking like this, and then I stop talking, but the audio keeps going.
So you're a telepath. I see.
Yeah.
I'm telling you what I'm gonna tell
and then
you.
I catch myself like, oops, I'm talking psychically. I better hurry up and use the mouth again to continue so that it's not obvious. We're
gonna do a
bad
show.
Trick. Is it now?
Bad.
This is the part that gets
It
edited.
was like 5
from the
minutes ago, I
podcast.
think, actually.
This is
See,
the
if you're
podcast.
listening here, this is what the podcast audience doesn't get to hear: is me derailing the show occasionally.
But how do you know that it wouldn't look like the video just froze?
Right, because you'd still have to gesticulate.
Oh, okay. So you're
Even
still
though
gonna
he's
be
not
moving around like you're
It's-
talking, but the mouth will just be.
Yeah, and then you'll realize, and then you will start doing the mouth talking.
We're gonna start this show in a 3, a 2. This is TWIS. This Week in Science, episode number 792, recorded on Wednesday, September 23rd, 2020. Where is the dark energy? Hi, everyone. I'm Dr. Kiki, and tonight we will fill your brains with friend zones, old sperm, and more brains. But first...
But first,
Disclaimer. Science. It's the reason for the modern world. Why medicine is a thing. How technology came to exist. It's a great collection of facts that have given humanity access to reliable knowledge. Reliable because it's derived rationally based on evidence and experimentation. Take the evidence of facts collected by thousands of scientists using the scientific method on the subject of global warming. Increases in atmospheric carbon, global temperature rise, warming oceans, melting ice sheets, retreating glaciers, decreased snow cover, rising sea levels, increases in extreme weather events, ocean acidification. Now contrast that with the politician who simply says, it'll just start getting cooler, you just watch. I don't think science knows, actually. And while not thinking science knows is nothing new amongst politicians, cigarette manufacturers, the fossil fuel industry, religion, racists, lawyers fighting DNA evidence, whoever's job it is to convince people to wear magnets, go on prepackaged diets, or avoid vaccinating their kids, none of these are reliable sources of information. Science works because it comes from the most reliable source of information humans have ever discovered, a combination of reality, rational, unbiased methodology of observation, and of course, This Week in Science, coming up next.
I've got the kind of mind that can't get enough. I want to learn everything. I want to fill it all up with new discoveries that happen every day of the week. There's only one place to go to find the knowledge I seek.
Good science to you, Kiki and Blair.
And a good science to you too, Justin, Blair, and everyone out there. Welcome to another episode of This Week in Science. We are back again with all the science that we fell in love with this last week that we just want to talk about because you know that is what we do. Oh, and we have got so much more as well in store. I have great stories tonight, some really exciting stories I am excited about. I've got microbial baby brains, wobbly rings, and arsenic because, you know, I like arsenic. It's great. Just a nice alternative. And we have a guest here tonight, Dr. Kevin Croker, and he's going to talk to us about dark energy and those geodes that we were so intrigued by several weeks back. Yes. All right, Justin. What do you have?
I've got COVID cats. Why Chicago is racist even after you die, and asteroid heading for the Earth. Also, it says it's heading toward the Earth.
Near.
Yeah,
Don't
it's heading
spoil
toward.
it, guys. Come on.
Yeah, spoiler alert.
Heading right towards the Earth.
Right
Turn
towards
the TV
us.
off.
I love you. I love this the anchorship of ruining the teaser.
Sorry, I can't.
The other
help
anchor,
it.
it's like asteroid heading towards the Earth. The other anchor is like, no.
No.
That's for our listeners who only listen to the
Politicians,
headlines and then turn off the podcast. We want to make sure they know.
But I did have the microbial baby brain story that you're bringing. Also, as I was going to throw that into the mix, I can't wait to hear this one because I just saw it and I just was like, oh, this has to be on the show. I love that you bring it. I can't wait to hear this one.
It's so exciting. It's
Blair,
really
what'd you bring?
interesting. Yeah, what's in the animal corner?
I brought really old sperm, like really old sperm. I brought
Great.
baboons in the friend zone and also stranger danger. So
I
Stranger
feel like all those
danger.
stories could be one.
Are these related somehow?
Yeah. They can be.
Could be. Maybe not. Hopefully not. But as we jump into the podcast tonight, I would like to remind all of you that if you are not yet subscribed to This Week in Science, you can find us just about any place podcasts are found, and you can find us on YouTube and Facebook and Twitch. Look for This Week in Science. But now it's time for the science. All right, first story at the head of our list. Wobbly rings. Do you guys remember that picture of a black hole that we were gifted with last year?
Yeah.
You have data from several previous observations of that same black hole that's at the center of galaxy M87, and a little like zhuzhing using math and computers. They've made a movie. They made a movie of the black hole now. It is not just a picture. It's actually with several images. It's like a GIF of a black hole. And in looking at this beauteous gift of black, looking at it, it's very obvious that the accretion disk of material that is around the black hole moves. That the gravity of the black hole and the forces that are at work, at play, make it so that it's not just a static object. You can actually see that there is motion, that there is energetic change over time. And this is a sequence of images that take place over about, I don't know, eight or 9 years or so that they took.
Oh, it's a long time.
Yeah, several years. And when I say mathematical computer science zhuzhing, basically they took the mathematical model that they used to create the most recent image, the image of the black hole. And they didn't have as many telescopes at work looking at the black hole in these previous observations. And so they took what data they had, and then they used the model of the black hole and put it all together. And so it's kind of simulated synthetic images in a sense. It's real data, it's real stuff, but it would not have been as pretty without the zhuzhing. This is astrophysics zhuzhing work. Very, very
So-
specialized stuff I don't know enough about, but I appreciate that they knew they had data from previous observations and they were able to take what we know and the stuff that was created, the programs that were created, the models that were created, and kind of work backward to give us more insight into this astronomical object.
What I love about it is the image that you're sharing on the video here looks like an eyeball. in space.
I think of it kind
It's
of like
sort of
it's a
like
wobbly hula hoop.
It looks like an eyeball that's looking around, and then occasionally has a light flashed in it because the pupil gets smaller.
I'm trying to figure out if
Creepier.
it's some sort of rotation, but it doesn't look like it.
And I think that's the question, whether it's the material in the accretion disk at the outer edge of the event horizon that it's getting energized, and so this is what we see.
Because this ring isn't the ring. It's not at the event horizon. It's somewhere in the middle.
No. This thing
But
is
it's
this thing is
other
sort of
outer.
Yeah, Kevin, you might know a little bit more about this.
you're looking at some sort of accretion phenomenon here. Is what most people are expecting this is. And so if there's whatever is sitting inside this object, it's this image. It's sitting in the dark region. So
Right.
There's something called the sort of innermost stable orbit for a photon. And so if you're a particle of light and you're sort of around this thing, if you're inside that innermost stable orbit, you're probably, you're not going to make it out unless you collide with something else. So things sort of get dark inside that region.
Right.
And so that's about, if I remember the number correctly, I think it's 3 Schwarzschild radii. So you're maybe, and the event horizon, if there is one, is sitting at 2 Schwarzschild horizon. So the object is sitting sort of inside the dark region by maybe about like 66% ish. I think I did that right.
So it's even further inside of the dark region.
Yeah. So it's
much more compact.
It's a smaller thing. Yeah. But it's interesting because the dark region is changing size too in these images, which I find pretty interesting. So maybe that even suggests that the object is even smaller on the inside. So you're seeing quite a large region of the accretion disk.
Yeah. I mean, it's just so, this is our first imagery of as close as we can get to a black hole, something that does not emit light. And so we're looking at the light that is around it, all the forces that are affecting it, and the fact that we've gone from just one image to now having this picture. It's pretty profound.
And the fact that it's not static, I guess, is part of the story too, because there's a turbulence of some sort taking place. Energies kind of going in there that may not have been expected in some models. So it's another paring down of there's models that won't fit this discovery. It would be pared down in our understanding.
Hopefully they'll be able to take more pictures next year. This year they were not able to because of COVID and people not being able to convene in the same place, and so the measurements that had been taken historically were not taken again. So fingers crossed next year people will be able to get together and take more pictures and continue to monitor M87 and other black holes that they might be looking at and give us more images, more close-ups on these incredibly dense, interesting objects in our universe. Yeah. All right, Justin. We're going to go from black hole wobbly rings to cats?
Yeah. Okay. So back in May, there was a 4-year-old cat living with a family that got affected by COVID-19. The family got affected by COVID-19. And somebody in the family died from it in the household. Then this cat started presenting a severe respiratory difficulty, breathing and such. And so they took it into the veterinary hospital. This is May, so this is still somewhat earlier in all of the pandemicness. And they were like, uh-oh, this cat has died of COVID or sick from COVID.
Yes, okay.
So they tested this. This is in Spain, hospital in Barcelona. It was diagnosed with hypertrophic cardiomyopathy, which is not COVID, right? So the cat dies because this is a horrible ailment. But they did confirm that the cat was suffering from this just hypertonic cardiomyopathy.
Wait, is this when the heart gets very large?
Yep.
Okay.
The muscle builds up.
Okay, so it's sort of like a chronic thing. Like it didn't happen acutely. It sort of built up over time, and the cat just reached some critical level, and then it was like, nope.
Just happened to die after all of these events were taking place. So that's coincidence. However, PCR tests did confirm that the animal had been infected with the SARS-CoV-2. So, but did not show any lesions or the typical symptoms or anything of the diseases that come along with COVID. So the only reason they tested the cat was because of this coincidence.
Right.
Otherwise, wouldn't have known. Serological tests on this cat and another cat that was also living in the same house showed that both cats had developed antibodies against SARS-CoV-2.
Right.
Quotivos. In both cases, we have detected neutralizing antibodies. In other words, they have the ability to bind to the virus and block it, explains Julio Blanco, AIDS Research Institute researcher. This is important because it shows us that immune system of cats can deal with SARS-CoV-2 and, in these specific cases, protect them from developing symptoms. So now we have two things going on here. Now we find out, okay, cats can get this, and they have an immunity to this as well in terms of any developing symptoms beyond it. Then the question is, how did the cats get it? Did the cats get it from people? Did they get it from other cats? So
and then the other question was, can cats then spread it to people?
Yes,
that was the whole thing happened in the zoo world, because they were like, "Oh God, put on all the PPE every time you go near a tiger."
So, right.
Felix
So
somehow have this thing. Yeah.
In this particular case, I guess these were very much indoor cats that didn't have access to other cats. So they don't think the cats caught it from mingling with other cats outside of the house.
So it went from human to cat.
Human to cat, yeah. Okay. So it's a reverse, whatchamacallit, when we get the disease from animals. Went the other way. The animal caught it from. So they tested the strain of COVID that these cats were positive for, and it was 99.9% similar to the virus that the owner had died from. So this was from human to animal transmission. Given that, but then the other question is like, okay, if cats are now immune, how do we figure out how they've done it? This is something we can try to recreate in humans in any way. Given the number of people infected worldwide and the very few reported cases of animals, experts continue to note that pets play a negligible role in the epidemiology of SARS-CoV-2. Cats can become very residually, it says, infected, and there's no evidence of transmission of the virus to humans. Although, really, who's looking? Who's going around testing asymptomatic cats to see if they catch it? And how, I don't think that they've actually been able to cross off cat to human transmission. This is not something that has been looked at enough at this point.
Just consider within a household. If the cats can catch it, then maybe it can go back the other direction. But perhaps if their neutralizing antibodies are strong, then they control. They get infected, but they control the infection fairly quickly, and then don't really spread it. Because if once the virus is neutralized, it's neutralized. It's not. It's not multiplying. It's not reproducing. It's not potentially getting spread back. So
potentially. But
potentially,
if they are residually still infected, it's just saying that they can perhaps still. So a cat-to-cat transmission might be difficult.
So what's your point here with this story? What are you trying to say?
Okay, don't get
wrap it up, buddy. Wrap it up.
Seriously.
Cat people getting defensive. It means that we need to look at this. We need to find out if cats can transmit to humans. Now, the thing about it is, though, cat transmission, cats don't seem like they socially distance themselves anyway for the most part. They don't go hanging out and snuggling up with
Do
strange
they?
cats.
Have you watched those little like videos where they attach a little like a
Cats
GoPro
love-
to the pet cat and it's like cat adventure and it goes around and like does all sorts of fun stuff?
Yeah, I mean
Makes new
they're
friends.
Has like little cat
Super
battles
spreader.
and like has like,
Yeah.
you know.
but it might be another reason to keep your cats indoors. Keep them, if Toxoplasma gondii isn't enough, just keeping
And the
them.
birds and the lizards and the frogs. Yeah.
Yes.
It's
But yeah, there
COVID.
is something to the
It's COVID cats.
story we've heard about cats being able to catch COVID.
Yeah, so
Yeah.
the three groups of animals that, at least as far as I know, animal people are worried about right now, besides, bats and pangolins, of course, is cats, mustelids, so like ferrets and weasels,
Ferrets.
and all of the like boar, pig, that whole family.
Mhm.
There is a report out of the Netherlands of a farmer who they believe became infected through minks.
Mustelid. Yep.
Mustelid. Yep. They're more worried about the mustelid farms themselves because those are money makers. It's farming.
Oh, so it's
For
not
the
just
person.
minks or vectors. The mink actually become ill and
They
can die.
they become ill and they
Okay.
die. And so if you have a mink farm that you're using the mink for fur or whatever, if the mink die off, then that's a financial loss. So yes, there's the question. Blair,
Yes.
tell me about your sperm.
No. Yeah. So Queen Mary University of London and the Chinese Academy of Science in Nanjing is an international collaboration and found the world's oldest sperm.
Singular sperm, like one of them.
Wow.
Like a group, whatever the collective noun for sperm
tangle.
is. And this was found in a piece of amber, which was from the Cretaceous period, which had a little tiny crustacean.
You're talking
named-
really old.
Yeah, named Myanmar cypress hui. And previously, the oldest known examples of sperm we have found have been 17 million years old. But this is looking to be hundreds of millions of years old, about 100 million years old. This is old sperm. So fossilized sperm is so rare, partially because it doesn't stay. It's not something that is easily preserved. So actually, it looks like the individuals in question had just copulated, and so it was very fresh.
And then what happened? Then what happened? Big thing of sap landed.
I guess, yeah. So
That's
these
right
things
off.
were
Yes.
these tiny little crustaceans
that's
are about
unfortunate.
a millimeter long.
But wait,
So yes.
you said these things are crustaceans?
Yes,
So where'd the sap come from?
Ostracods.
If they're underwater.
a branch. I don't know.
That's a great question.
No, they were
Yeah.
honestly, they were probably out of water for foraging or something. Think about hermit crabs. They're crustaceans that do spend time out on land. So
Okay.
that would be my
this
guess.
is-
Is that they climbed a tree that was near a water source to eat leaves or something. I don't
Come
know.
out of the
Okay.
ocean one
Yeah.
day for
Yeah.
one thing, and
Yeah.
this is why we stay in
Sorry.
the water. People,
So
this is
this is the last little twist of this story that I absolutely love is that oldest sperm, teeny tiny little crustacean, 1 millimeter long, giant sperm. So there's implications here because giant sperm, the other animals we've talked about giant sperm in are things like fruit flies. So most animals, including humans, produce tens of millions of sperm, teeny tiny little sperm in huge quantities. They're playing the numbers game. But
Right.
fruit flies and crustaceans like these are famous for making large sperm, giant sperm, to compete with one another inside of the female. So it's all about the strength, not the quantity.
Now, when you're
Right?
saying large
That's a
sperm,
love
how
that
large is the
sperm.
large sperm?
Tiny, still very tiny. You need a microscope. But just compared to our sperm, really big. And so, because, these guys are only a millimeter. big. So they're still teeny tiny. You still need a microscope to see them. But the interesting thing here is that fruit flies, current modern day animals that we found giant sperm in, scientists have previously thought that this was kind of a new, kind of a novel evolutionary adaptation, this giant sperm, but it was around 100 million years ago in the direct line of invertebrates. And so there's an idea here that this was conserved over evolutionary time. And so the idea of giant sperm is actually very old and very successful. So this has implications for our study of reproduction overall. But yeah, also just the oldest sperm ever. Very cool discovery.
Wow.
It's amazing. And the chance discovery also. I mean, the chance that it was preserved and the chance that it was found, and then to be able to realize what they're looking at. And yeah. Yes.
Do people just sort of like look at, like, they find amber, and the first thing you do when you find amber is like, what's in it? And then you like get this. Okay.
Absolutely.
You're like, I think this is old. Take it back to the lab.
Yeah, there's actually like there are issues. There was an article recently about, they were calling it blood amber, similar because the amber is they're using human labor that is not compensated, and similar to the idea of blood diamonds. But blood amber is a big field, and the amber very often is scientifically interesting, and so there are potential ethical landmines that are involved in using things like that.
Yeah.
This
There's one of those things that there's an argument for scientists to partner with illegal operations, illegal dig sites, the blood amber, just to get those specimens out of there, just to get the views or record where things are pulled from. No, really, we talked about this also when we talk about the sort of archaeological site looters or illegal fossil trade, where people are doing digs in sites that they're selling them. You know, having an archaeologist who's in that world, who can at least record it before it disappears and is untraceable to whence it came from.
So it would kind of be like an undercover scientist, like you're just in the world. Yeah,
a little Indiana Jones.
I don't know about that.
Sort of black market recording.
It's not the years, it's the mileage.
So I wanted to say, because the internet will get me after this if I don't have this little addendum here. So I did a quick Google. And just to let everyone know who's itching to know, a human sperm cell is about 50 micrometers long, so it's teeny tiny. But a fruit fly, a Drosophila sperm cell, is 5.8 centimeters. So it's coiled. It's super duper coiled. I did not know this.
How do you
or if I
fit
did
it in
know,
the
I
fly?
forgot it.
Like, where's it stashed?
So it's just it's really just coiled up and teeny. I pictured kind of like those little grow things you would get as a kid that were in the little pill, and then you would
add it to water.
So I'm picturing it's kind of like that, except it's just coiled.
Do you just give one of them to the female?
Yeah.
Like, here it is. You know, like, here's the giant sperm.
Yeah.
Take it.
Is this a box of chocolates? It's not chocolate, but we'll open it up later.
Yeah, so they're coiled and they're delivered to the female in a tangled coil, and then they expand inside. So there you go.
Fancy.
Yeah.
Very fancy. It's like, spring. Anyway, for those interested in the number pi, you might love this story. There has been a new exoplanet discovered that orbits its star in just 3.14 days. That's right. Its orbital period is very close to pi. So it's not exactly pi. I mean, pi, you could go out to more digits. But anyway, close enough. The astronomers from the Kepler-2 mission who have identified this exoplanet, they thought people would like it because everybody likes a little bit of fun. So this is data recorded back in 2017 by NASA Kepler Space Telescope's K2 mission. And using this looking for this potential planet. They used ground-based telescopes in Chile's Atacama Desert called the Search for Habitable Planets Eclipsing Ultra-Cool Stars, otherwise known as speculoos. And they confirmed that there was this Earth-sized planet. It is 0.95 times the radius of Earth's, and it's orbiting a low-mass star, smaller than the sun. It's orbiting very, very closely and very, very quickly. Still, even though the star is cool and it's orbiting fairly closely, it would be too hot for life to exist. Although they do think that the planet has a rocky core, very similar to Earth's, so it might be something very interesting to study for potential habitability of other planets and how exoplanets, unlike those planets in our solar system, are evolving and moving through space and time. Yes. Pie. It's the pie planet. We can go there and have pie. No. Justin, tell me about this asteroid.
So there's this small, it's called a near-Earth asteroid. It's about the size of a school bus, and it's heading towards Earth.
Is Miss Frizzle on it?
I was going to ask
You might be.
question.
Yep. Yeah. Thankfully, it will not be making a stop here, as so many of Earth's schools have been closed due to the pandemic. It will be zipping by Thursday, September 4th, which is tomorrow, some of your time, later today, my time, I think, at a distance of about 13,000 miles from the planet's surface, which I don't know if... yeah.
I mean, that sounds great. It's not close. It's close, but it's not.
That's very close. So
how close is the moon? I think the moon is.
I know
moon
it's
is
further.
like 200, 400,000 miles. It's up there. The satellites that we have in geostationary orbit are 22,000 miles out. So this is
where do
coming
we have
in.
to be to see this thing?
So
Yeah.
great question. To see it, it's probably
Did you say that it was 13,000 miles?
13,000.
So it's going to come closer than geosynchronous orbit?
Yes.
Yes, it's about halfway point of geosynchronous orbit, right in between. Woo! Underneath satellites. Bzz, zipping by.
It is
So
zipping.
Sounds like 2020 to me.
Yeah.
yeah, doesn't it? Except that it's gonna miss. Except that it's gonna miss.
Is
And
it?
Justin, don't jinx it, please.
So here's the thing. Even if it hit the atmosphere, this thing is about 15 to 30 feet wide. If it did hit the Earth, it would likely break up in the high atmosphere, becoming a bright meteor known as a fireball. So these things apparently hit once a year, once every couple of years. It's not completely off the map for this size of an object to be hurtling towards and actually hit the Earth's atmosphere. So we're safe even if it does, if the projections are off by a bit.
But what I can do is turn off all of my devices tomorrow and just say to my boss, "Oh, I'm sorry, I didn't have internet. The satellite got hit by an asteroid the size of a school bus. I'm sorry, it was out of my control.
Sorry, I had nothing to do with it.
It's true, my Netflix still worked, but otherwise, I was unable to do anything."
Yeah, if it actually hit a satellite, that would be pretty amazing shot. It's going to make its closest approach at we might not be able to see it, 4:12 a.m. Pacific time, which is 7:12 Eastern time, which is
A little bit before when I wake up.
A little bit.
about what is that? That would be about 1 o'clock ish Central European time. But it's going to be visible, I think, for possibly if you had the light to see it, or if you had the telescope, maybe over the Southeast Pacific would have the sort of facing view as this thing zips by. So
I hope somebody's on an
Coast of
airplane
Peru,
who can take a picture. Nope, that's not going to happen. Never mind. Thanks, COVID.
So there's
I felt that one.
I know.
I did hear they're doing trips in planes now where you don't go anywhere.
Yeah,
You
they
get
just
on the
fly
plane,
around and
you fly
drop
around for
down
7 hours, and then land at the airport where you started. So
When
That
you miss
sounds
that experience of being that close to the next,
yeah,
you just gotta feel it again. You know, it's
and
If
have
you're
all your
going-
friends there ready to welcome you.
I'm sorry.
Hey, you're back.
If you're going to take the risk of getting on an airplane in the first place, actually go somewhere, please.
Also,
Please.
if you're going to produce the carbon emissions, please go somewhere.
Oh my goodness.
So there is something along the lines of needing to keep the planes running to have them well maintained, which is an important thing. There is, and apparently the folks that have been opting for that have just been like, yeah, let's go see our home state from the air. That might be fun. Let's just look out the window with a nice view and circle around and see everything, like a little sightseeing adventure. I kind of get it.
Right.
I like that. Anyway, this finding is they say there's over 100 million of these small asteroids, like the schoolie that's going to go by on Thursday. But they're small enough that we will only ever have a couple days warning at this point that this thing is coming by.
We won't see them otherwise.
Yeah,
but they're
although
all you said they're gonna pop in these fireballs, so this size is not so troublesome.
Yes, but this is part of the system that's allowing us to see the larger ones. We're looking for things that aren't, 15 to 30 feet, but maybe more in the 460 foot wide or long size. So this is part of the system that is looking for the earth-ending threats, the larger asteroids out there that would actually impose a really big problem for the Earth. This is a small one, but I like to know that this is taking place, that we do have eyes on space looking for these things. We can even tell, based on the trajectory, that this thing's coming back in 2041, at which point it will make a more distant flyby than it did this time. But yeah, we are...
Stay away.
Stay away. Yeah.
We are tracking these objects in space.
We're trying to track the objects in space. We're also trying to track life back through its history. And at one point in our planet, there was no oxygen, but there was life. So
oxygen was the first extinction event.
Right, it was. There was all sorts of life before oxygen really became this thing that, we're like, I love my oxygen-filled air. At one point in time, life was like, no,
that's toxic.
Toxic, yes. So the question is, what did those early organisms rely on? There were photosynthetic organisms that were chemoautotrophs, where they were relying on chemical energy. There were also organisms, they think, that were photosynthesizing, but without oxygen. Oxygen takes the role of the electron carrier in photosynthesis. And there are other elements that can take its role. And many, like 2008, there was evidence of bacterial use of arsenic. And they've been looking into it ever since. And there's now a paper published in Communications, Earth and Environment by a group out of the University of Connecticut about their research looking into microbial mats that were found up in the Atacama Desert. So we're talking about the Atacama Desert, where we're doing telescope observations of the universe. We're also finding bacteria that are living in this really dry, low oxygen, high UV radiation environment. And they have found these mats that apparently are, they say, the best thing to be looking at to be approximating the study of what life was like when it first got its start on the planet. So it's high sulfur. There's water running over these microbial mats. The microbial mats are in this kind of stream environment that has zero oxygen, completely hypoxic, anoxic, no oxygen whatsoever. And they think, to date, what the researchers have said is that every time they're looking at microbial mats, that researchers are like, oh, it's like life before life, began the way that we look at it today. The researcher's like, no, not really, because all these microbial mats you're looking at, they have oxygen in them. We found one that doesn't. And so So now they think that they can really look further at the processes that are in place in this high desert, high UV, high salinity, high sulfur, zero oxygen, high arsenic environment, and really verify how they're working. Maybe the beginnings were arsenic based. Poison is love. Poison is life.
Well,
We're need dandelions, I guess.
Yeah. Yeah, so it's fun stuff. Arsenic, instead of arsenic and old lace, it's arsenic and old
life.
Old life. Yep.
Old lice.
Oh yeah.
Old life. There it is. Okay, moving into the present. If you just tuned in, you are listening to This Week in Science. If you are interested in a TWIS shirt or mug or other item of our merchandise, you can go to twis.org and click on the Zazzle link. Browse our store and find all sorts of items that will show your love for TWIS and also help us out. All right, I would now love to further introduce our guest tonight. Dr. Kevin Croker is an astrophysicist at the University of Hawai'i at Mānoa, where he's studying dark energy and objects like neutron stars and geodes. And he recently authored a paper on geodes that we discussed on the show a few weeks ago. Thank you for joining us on the show today.
Thanks for having me. It's I don't usually get to do something like this, and so it's pretty exciting. So.
Well, we hope that you're having fun so far. And now that we're really going to start asking you questions, we hope that you continue to have fun.
This is it.
All right, bring it on. Let's do it. Let's do it. Bring it on.
So I introduced geodes a few weeks back, but, just for yourself, how did you get interested in your field of study in astrophysics, and how did you kind of come to focus on things like neutron stars and these dense, weird objects in space?
So, do you want the sort of real big picture? How far back do you want to go here?
As far back as you want to take it. Yes.
I guess I should just say that at undergrad, I didn't formally study physics or astronomy. Mm-hmm. I was a computer scientist. So that's what I was, sort of CS engineering type stuff. But every night I used to get online and read the phys.org or whatever. Yeah, they're not paying me, I promise. I used to read what I call the hot sheets, right? Just to see, what was new, what's going on. Things like what you guys are doing here. And so I was really interested in this sort of thing, but I felt that it was not accessible to me. It was a very far reach at the time. But I got into Richard Feynman. He was really a strong popularizer of science, and his professional work is held in quite high regard. And I just really liked his stories. I really liked the guy. I was like, this guy's pretty awesome. He's got a pretty cool life. I wonder if I could do something like this. And so after I finished the CS thing and spent a couple years at the radio station, I sort of taught myself some physics and basic math, the calculus. I had to do algebra and calculus again on my own because I'd forgotten it. And I sat in on some classes, and professors were kind, and they wrote some letters for me, and I was able to get in out here in Hawaii, and that's how I got here, and that's how I ended up doing physics. So I came out here because there's a world expert out here on what's called weak scale supersymmetry, a guy named Xerxes Tata. And sort of before LHCs didn't sort of find evidence, or at least immediate evidence, for this model called weak scale supersymmetry, I was definitely looking like it was really, really going to be viable. It was something that was going to be very relevant. And so I decided that this would be sort of a good place to be. I ended up with a different advisor that does neutrinos, which are these very tiny sort of fragments of a nucleus. Is one way to think of them, and they don't like to interact with matter very much, and so they carry a lot of interesting information that you can't get other ways. And he always hung out with the astronomers up at the institute, and so because he was hanging out with them, I ended up hanging out with them, and they worried about his particular friends, I guess, worried about large scale stuff, sort of cosmology, big things. And so that's where my research topic eventually came from. I was worrying about very, very, very large scale stuff, like the biggest scales you can get. Something called the initial condition problem. So you have the Big Bang, sort of the universe started in some very dense, hot state. And then you can always ask the question, okay, that's great, and it agrees with all the data. Where did that come from? Or what happened before that? And so a lot of people will dismiss that as sort of like a metaphysics issue, like this is, beyond testability or whatever, but it's not. And so people have started to worry about these things again. And so I was initially sort of working on that idea, and I was trying to sort of construct like almost like a biologically inspired model. So instead of saying, it just started in a bang and we're not going to care about what came before, because then you have the issue of sort of specifying like what was initially there in order to get the equations to specify everything else correctly downstream. You can just say, well, there was a universe before that. And what was before that? Another one before that. And so this idea is not mine. It's been around in Russia for quite a while. And so I was playing with ideas like that. And I was trying to build a model that worked in sort of a more precise way. And I just was failing. I couldn't do it. It was pretty hard.
A lot of people have failed at this problem. This is one of those big questions of how does it all fit together?
I love it.
It's not failure. It's just we don't have
to figure out what the universe was like before the universe. I failed. It was. I really disappointed myself.
I shot a little too long on that first one. Didn't get there. Yeah. So. So what happened though is I'm writing this model down, and I expected to find something that would look like dark matter, which is another one of these problems that we're dealing with right now. And instead, I kept getting these regions of dark energy, and these small regions of dark energy, and I was like, that can't be right. This is, that's not the way I thought about it in my head. And then I just sort of thought, well, wait a second, what would happen if you did have something like this? And I just ran really quickly the numbers just on a envelope calculation, and it was sort of off by a factor of 1,000, which sounds pretty awful. But the sort of leading explanations for a cosmological constant that don't work are off by about a factor of 10 with 120 zeros after it. Mm-hmm. So going from 120 zeros to 3 zeros felt pretty good to me at the time. Yeah. And so I wrote like a real quick paper and like pushed it off to some journal, and they got back to me pretty fast. They're like, yeah, that's a cool idea, but do a damn calculation. And so, so that's how I got started on this, was, this weird coincidence that I wasn't expecting to find. So I didn't know so much about the dark energy problem at all, or any of these things, because I was worried about sort of something unrelated. So I sort of came at this problem from a very different perspective, and that ended up being somewhat useful down the road. Did that address your question? I kind of went for a long time. I'm sorry.
No, it absolutely does. But so you're coming at dark energy from this different perspective of, where did the universe come from? Where did it all start?
But it led down to this very small thing. So I was sort of focusing on extremely large stuff.
Yeah.
And then I found out that you get these really small things, and they seem to contain the stuff you wanted sort of to get at the pretty big but not ridiculously big stuff. So it was this weird connection between very, very, very vastly separated scales. And that's weird. That's odd. And so that sort of caught my attention, and I kept playing with the idea. So, and
when you start looking at dark energy, though, what, Justin?
I have heard that.
What, Justin? Come on.
Yeah, I know. I have heard that the universe is connected from the macro to the micro scale. Like, it is all one continuous universe. It's the same universe. So if you are I mean, I'm just saying.
No. I mean, yes, I agree we're in the same universe.
I'm doing this stating the Captain Obvious thing here, but that finding a phenomenon there should be something that connects the very large observation to something that's actually taking place on the minutest of scales. It has to be built on this foundation in the first place. So if what you were looking for,
I'm really glad that you feel this way, right? Because I felt this way as well. But a lot of other people don't. And it was very difficult to sort of figure out why. So I'm really interested to know where you were sort of exposed to this idea, or where you developed this intuition.
Oh no, it's good. So isn't
Right
this
now?
the argument? Isn't this the argument between? Isn't this the argument between sort of quantum physics and more like people who are looking like that scales have disagreements in how they are able to calculate things, but they have to be connected because they're all phenomena built on phenomena built on physics all the way down. So it has to be connected. There's no way that you go at this scale that everything just completely changes and has its own rules and doesn't care what's happening at the other scale of the universe.
So I should make a disclaimer first that the sort of the things that I work on and the frameworks within which I work are Einstein's theory, general relativity. So, and I really, last time I worked on quantum mechanics was years ago, 8 years ago or something, like just in my studies, right? Not with respect to any sort of research. So I'm very much a relativist and a sort of a very bad applied mathematician, maybe you could say. So I'm not qualified to speak on anything that has to do with quantum mechanics. So I just sort of work only with general relativity. And the way that sort of I would call classical theories, sort of stuff that happened before the advent of quantum mechanics, are usually regarded is that they sort of have this property called locality. And so whatever is happening here and whatever is happening here, like if they're going to somehow interact with each other, there has to be an interaction that sort of propagates at most at light speed. And so you can have these delayed effects, but to have some sort of non-local correlations or things that are sort of happening at the same time, but at different places, that notion is actually can be ill-posed in classical theories. And so most people's expectation within a theory like general relativity is that you really shouldn't have effects like that taking place. And so that's why dark energy is actually somewhat interesting, especially with the way we went about doing it.
Yeah, so let's talk about dark energy for a minute. That wasn't your focus, but dark energy in the way that we understand it is we really don't know what it is. We know that it is a force that it is involved in the expansion of the universe.
Well, to say that we don't know what it is so there's sort of, it's good to separate the observational evidence for a thing from the thing itself. Okay. And so the observational evidence for the thing is sort of coming from a couple of different places. So you've got the evidence from supernova that are pretty far away, and you build this distance ladder where you sort of bootstrap your way up looking for parallaxes, so stars kind of move around like this, and then you can get the distance to these poofing stars called Cepheids, and you can see Cepheids further out, and then you get the distance to those, and you can use the distance from the Cepheids, and you see these exploding stars that are really bright. And then you can see this much further out because they're much brighter. And so you can sort of build this scale of distances out. And the supernova look sort of dimmer than they should, which sort of tells you, if you interpret it that way, the easiest way to interpret it is that the universe is expanding faster than you thought it was. And that was sort of the first observational evidence for the phenomenon that has been attributed to dark energy.
Got it. Mm-hmm.
Okay. So, and then consequently, there's other evidence has come into play. So you can sort of look in the sky and look at where galaxies are, and you can sort of ask questions like, if I have a galaxy here, and I draw a circle that's of a certain radius out from that galaxy, what's the probability I'm going to find another galaxy in that circle? And you can sort of answer that question for many different radii of circles, and then you can play that game at every galaxy you pick on the sky. And so then you get some sort of average description of the probability of, if you're looking at one galaxy, how likely is it that there'll be another one nearby? Right. And so you look at sort of data like that, and that sort of gives you information on the expansion history of the universe. And you find that the way that that's set up is suggestive that you have a certain amount of matter in your universe. And that matter accounts for maybe 1/3 of the total energy that you need in the universe. And so there's sort of like a missing 66% that should be there, but it's not acting like matter. And so it turns out that number works with the same number that would cause the brightnesses of the supernova to be dimmer as much as we see them to be dimmed.
So can I real quick? When we're talking about matter and energy, the energy that's in the universe, are we talking gravity?
Okay, no. So this is actually a really good point you bring up, Justin. And there's sort of like a language issue, and sort of the names dark matter and dark energy are pretty unfortunate names. In fact,
they're placeholders, right?
Yeah, they're
just
placeholders, but they sort of you're easily confused because you hear, about Einstein and energy is mass and all these things, and so you think that energy is matter, and then like how dark energy and dark matter are different. It's sort of in the mind. It doesn't keep the concepts cleanly separated when they actually should be. And so I think it's funny that the original name for dark energy was not dark energy, right? Of course, it was something called mu vacuum. It was called mu. So this Russian guy in like a Siberian prison camp in like the 60s wrote a paper about how you should expect to find there should be material that he called mu that should have very strange properties, but it should be there. And so this is sort of another example. So I gave you two examples of observational evidences: the supernova and the brightnesses, and the sort of what's called the turnover in the matter power spectrum is the phenomenon I described before. And so there's also sort of the theoretical argument that you should have material like this. You can sort of play a mathematical game with Einstein's equations, and you find that most things that you know about sort of fall into a certain category 1. But then light falls into like a category 2. And then there's there's a 3 and a 4 that are totally crazy, and you don't worry about those. But it turns out you can ask, like, okay, what are all the possible things that fit into category 1? And there's one thing that's very strange. And we would call that thing now dark energy. But it's like a material. And so he's like, well, we never seen anything like this before. But then he goes and talks about,
Oh
He's
no!
frozen.
We have a freeze. What happened?
Kevin has been frozen. But thankfully, Kevin is
about.
But look,
He's
Kevin's
telling us a
pretty
great
photogenic.
story.
This is
He's
how you
very
can tell.
photogenic.
Yes, because he looks decent. Whenever I freeze, because my face, I think, moves so much when I talk, it's always in the middle of a micro expression that's just terrible. So that's, Kevin, if you didn't know before, you're very photogenic.
It's good of you to tell him.
Well, you can't hear. He's stuck in the ether at the moment.
Either. Everything was great up until that moment. The internets. Oh, the internets. What if I remove him?
Yeah, we're going to have to message him and let him know to come back and pick up right where he left off.
Right. Exactly where he left off at that specific
explaining how this missing matter, this unseen type of mystery matter.
He has friends in our chat room. Star. Thank you for sending a message. I sent a message as well. He'll be back and we will continue to learn because we are learning. Kevin, I did knock him off and I told him, yes, the internet, there's sometimes nothing you can do about the internet. It's just how it is. This is the part of the show that's
But one of these things,
a school bus-sized asteroid? I'm just curious.
A school bus-sized asteroid? It's the size of a school bus.
Is that what happened?
Was it?
Too soon.
Yeah.
Too soon. Too soon. It won't be by for a few hours. Yeah.
Yeah.
One of the things that I do always find fascinating is when it's like really hard for people to understand that there's this phenomenon that we recognize in the universe, which is this dark energy, and the one that is dark matter, that we don't have a physical mechanical thing. We say, hey, this is that material particle that's doing this. We have that issue with gravity. Gravity, we can absolutely calculate its effects within the
We know
universe.
how it works. We don't know.
We can land ships on foreign planets. We can predict the motion of an asteroid the size of a school bus and when it will be back and how far. We can project all of these things based on our understanding of gravity. We don't know what it is. We don't know how it communicates. We don't have a physical thing that's like, this is the mechanics of the gravity particle or the gravity wave. We don't have that yet, and yet we understand that it exists. So I think at some point we will get closer to that. But in the meantime,
Yeah, we're done. I
We can call
mean,
it
the
dark
more
gravity.
we look, we're gonna hopefully. I mean, I hope at some point in humanity's future we solve these problems. I think if we keep looking, we'll uncover this kind of stuff. But at the same time, he says he should be back. He's working on it.
because I have two dumb questions to ask
Working
him
on
now.
it.
There's no
Dumb
subject.
questions, but don't go off. I want to talk about geodes. Let's not
Okay.
go off in the weeds. I've got to talk about the geodes.
Am I in the weeds? I don't know that am I in the weeds?
I want to. We're gonna steer back.
I don't know am I in the weeds? Okay, I'll be right back too. I'll be right back. I'll be in the I'm gonna go to the green room for a minute.
You're going to the green room. Bye. Blair, you look so excited. So
I'm trying to decide. Should we try to do something else?
right, that's always my my spot sitting here is should we keep going with stories and other things when we will end up having someone come back in, hopefully, and if they do come back in, then is it going to interrupt and will we have to start over on the other stuff or what should we do? But now Justin's going to take a break, so maybe he won't have to take a break later.
That's true.
Yeah, it's 2020. I'm not surprised, Lightning Rod. No. And yes, in the meantime, smash that like button if you want our guests to come back. You want Dr. Croker to come back, smash that like button right now. We're going to keep doing this podcast. That's right. Time for an AMA, Shoe Brew.
Mm-hmm.
Sai says his connection is back. So let's see if we get him back in here. Todd Nielsen, great to see you in the chat room. Hello. Anunnaki, hello. Yes, hydration. Get the hydration in there while you can. We don't want to break your screen flying out. Not smash it with rocks. Smash the like button with your thumb. Boop, boop. I did not hear about dark bosons today, Shoe Brew. I did not. How's the geo thing spelled? Like geode. 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 It stands for. Hold on 1 second. I got it in my. Oh, Kevin's back. Woohoo! Bringing him back. Here we go. Welcome back. We're glad to have you join us again.
So I'm actually a new person now.
That's right.
All right, can you hear me?
Sure.
Like, is
Yes.
this? Are we working? Okay.
Yes.
Where did I don't
All
see
good?
Justin? Did we lose him?
Oh, he went and took a break.
I wore him out.
He said, "I'll be back." Get into it.
So yeah, there was. I'm sorry for the extended delay. I don't know what cut out, but then I have the window smaller on my machine, and so there was a button that said "Enter the broadcast studio" that was not displayed. So I didn't see that. I had to click the button in order for you to be able to let me in. Yeah, so I'm very sorry for that. It's my fault.
You figured it out, though. You're here.
Live show. These things happen.
We've done, yes. Sai is in the chat room. Thank you for answering the question about what GEODES stands for, generic objects of dark energy. Yes. And at some point...
Did Sai identify himself?
No, just said Sai. Somebody who knows you.
I try. I think that they're a very reliable source, so that's good.
Okay, good. I hope so. All right. So you were in the middle of telling us about the Russian and how he was looking at all these things and
Playing
basically
with mathematical games. Yeah,
playing
he
the
was
mathematical games.
Yeah,
Yes.
he was just playing mathematical games.
Yeah.
So his name is Eros Gleaner. By the way, he's still alive. He managed to get out of the USSR and end up in San Francisco. So he's in some sort of elderly care facility. So I think he's pretty old at this point, like 98. But he's still kicking. And yeah, a pretty impressive person. He only has one arm also. So here, let me try to put this there. Okay, that should be better. Sorry. So yeah, I a little bit derailed, so you'll have to sort of reorient. So we're talking, guys, about what he called this stuff as mu, this mu material. And it's just a sort of a very strange type of material. So yeah, stuff was predicted to exist a long time ago. And as usually happens in physics, you hit on sort of a useful idea pretty early. But the data is just nowhere near there yet. There's no evidence for it. And so it sleeps for a while and then comes back up 20, 30, 40, 50 years later. And so dark energy was one of these things. So the way that I guess it picked up the name dark energy is you would not usually expect, or you would not welcome back. You wouldn't usually expect sort of a phenomenon to happen like this mu material. So Gleaner thought that it should happen during gravitational collapse, when something is crunching down, that eventually everything like squishes into everything else, that you would form this mu material. And so it wasn't thought, for various reasons that are actually very, very technical, and that these localized regions of mu material would somehow conspire to produce like a large scale sort of effect. And so I guess we should take a step back. I should ask also, are you guys with me with respect to this notion of dark energy as just like a type of stuff, but just a different type of stuff? Okay. So, and then I guess the chat window told you guys that GEODES is generic object of dark energy. So it's a ball of mu material, and that's it. So just like the moon is a ball of rock, and a star is a ball of very hot gas, it's like a nuclear fire, and a neutron star is a ball of neutrons. A geode is a ball of dark energy, and that's it. There's nothing else sort of crazy to it except the properties of mu. Mu material is really weird stuff. Yeah.
So when I came across your paper that was recently published, and the idea that and last year's paper and things talking about this idea of geodes, the concept of a black hole is something that people are fairly familiar with at this point.
Sure.
It's like, okay, matter collapses down, and then at a certain point it smashes all up. You have event horizon, light doesn't escape, you've got weird effects of the black hole, but that's just a weird black hole thing. And now you're saying that some of these black holes can actually be a different, maybe they're matter that's black hole in the way that we would describe it normally, and other times maybe it's this mu material, or is it always mu material?
So that's actually a really good question. There are some models that say that you could make a black hole, or you could make an object, like a mu object, that would also have an event horizon, and you can make ones that don't. It really is sort of black holes are sort of funny objects, because they're sort of characterized entirely by maybe three things. They're characterized by their mass, they're characterized by their charge, if they have any, and they're characterized by their spin. And those three numbers suffice to like give you everything you can ever get out of a black hole, at least if you're not playing Hawking games. And that's sort of why why black holes are a problem. And people think that it's a very interesting thing to study, is because you have all this sort of stuff, information going into this object, yet somehow all of that's broken down or digested in just these three numbers. And that's troublesome in various ways, and people have really worked on this for a while. So you don't have to always form a black hole. You don't always have to form a geode. These are sort of, we don't know. These are sort of solutions that are admitted by Einstein's equations. And on the outside of these solutions, like outside of anywhere any funny business would be happening, they sort of look the same. And so as far as observations can distinguish them, like local observations, people thought that they were the same, basically. And so they didn't bother making a distinction. And it's much easier to work with the black hole solutions. Like as a mathematical thing, they're far less complicated. So black hole solutions, if you go very far away from them, they exist in isolation. If you go very far away from them, there's nothing out there and there's nothing happening. And that really simplifies the math. And
black holes really, it's gravitation. And so if something's close, it's going to get pulled in by gravity, but gravity falls off kind of with distance. And so
the thing that's interesting about a black hole, you said something that was actually very correct, that the classical black hole solutions are what are called vacuum solutions. So you don't have any stuff, yet somehow it acts like there's stuff there, but you don't have any. And for instance, the way they found the spinning solution, the Kerr solution, which is the one that LIGO fits the waveforms against, the question that was posed was, what's the only way that I can sort of make a thing that if I rotate it in some direction, it looks the same and there's nothing special going on away from it? What's the only way that I can describe a universe that has that property? And the answer was the Kerr solution. And so there is no description of any stuff. There was no sort of dynamical process where things were collapsing, things were accreting, the pressures built up, and there was a conversion into a spinning black hole. It's just, you got this thing. And then people were like, well, if this is a real object, then something like this has to be able to form somehow. And then people, added on ideas like that. But there is, to my knowledge, no fully dynamical model of the formation of any objects like this at all, whether it's geode or black hole. So people have done sort of, just really, really toy models where you have a bunch of like a spherical cloud of dust coming together. And by dust, I actually mean it's pressureless. It doesn't sort of smack into itself and it just sort of collapses. I mean, there's models like that, but I mean, you just saw the wobbling ring around the image of these things. That's nothing at all like what's going on, right? So
there's obviously a lot more complexity than these models, these vacuum models.
Yeah, it's the problem with the mathematics is Einstein's equations are just so gnarly that you really, in order to make any progress at all, you got to start as simple as possible. And
isn't there some sort of a joke where a physicist is asked to describe a cow and then says, okay, picture a cow as a completely spherical object. Let's start with the most basic. Get rid of all of the leg, the ear, the thing. Just
it's a spherical cow.
Yeah.
And I mean, the spherical cow would probably, but the spherical cow it can get you a lot of like a good, I can't speak English right now. The spherical cow can do a lot for you. There we go.
Yeah, it's a close approximation.
Yeah, you can figure out maybe how much methane a spherical cow produces. So.
But how will a spherical cow help you with black holes and geodes? That is the question.
And so the answer, at least to me, was it won't. Yeah. And so we had to sort of figure out a way to deal with that. We can't play with spherical cows if we're going to be in a real universe and we're going to deal with real sources. And these sorts of problems were beyond me. And so I had to team up with a mathematician, and and we worked pretty hard on this for a while, and we've been making some slow progress. And that was really the sort of the thing that matters the most, was sort of figuring out how to go about dealing with these what are called very strong sources in Einstein's theory without making the approximations that are usually made when dealing with strong sources locally, like when looking at their mergers, when looking at things that are accreting onto them. And that was the hard part, sort of how to get these sources into like a bigger picture that fit together into a coherent whole. And that's actually what the 3 papers in this series do. So the first paper in the series that you mentioned deals with sort of the base level of the calculation. And so the strategy is to sort of, instead of, all right, so we take a step back again. Usually the way physics is taught in school, like you guys had it in intro physics, is that if you understand the way the parts of a thing work, and the parts are simple, then you can sort of piece together the parts, bit by bit by bit, and build up a very complicated thing. And if you understand how the parts work, you can understand how the whole works. Mm-hmm. Sort of this intuition, or this sort of approach to a problem, is physicists usually attach a word to it. We call that linear, right? So if you know the parts, you know how the sum works, and that's linear. And a lot of the things that we have, a lot of the theories that we have are actually linear. So electricity and magnetism ends up having this property, and that's really nice. And so we can do good things with it very quickly. Newtonian gravity also has this property, and so it's very nice to work with. Quantum mechanics also has this property, and so it's very nice to work with as a formalism. Einstein's general relativity does not have this property. It's not linear. And that's what makes it so hard to work with. You can't sort of use techniques you can't break the problem down into little chunks and then build up from those chunks. And historically, working with general relativity, people have attempted to do that anyway. And the reason is just that that's what we know how to do, right? And, what else are we going to do? And so what I worked on with the mathematician was really trying to figure out a way, instead of like going up from the little bits and trying to build a big structure, how to actually come from the top down and sort of start like in very broad sketches, and then step by step refine the picture, sort of like you would like if you were making like a piece of artwork or something. Mm-hmm. Or, back in the day, like I'm going to really date myself here with age, but when you had a modem and you were downloading an image on the internet, and sometimes there'd be the images that would come in line by line, right? But then sometimes there would be images that would come out like really blurry. And then the blurriness would like resolve into sort of like blockiness. And then the blockiness would resolve into sort of like, just sort of a rough blur. And then it would sort of come into the full resolution image, and it would come into these stages. Mm-hmm. And so the approach we took with Einstein's equations was exactly like that second way of storing an image. And so we sort of build the calculation in layers, and each layer we make a further refinement on the previous layers. And we found out a way to do this that allows us to sort of incorporate very, very strong sources in a way that's agnostic to the fine details of the source. And when we did that, the first step of the first layer, when it's just a uniform color, it's not just black, it's some uniform color. That first layer, we found that the strong sources are effectively smeared out. That the dynamics, the behavior of the universe you expect in that coarsest, most average sense really does require a smeared out version of all the sources that you have present. And that's a really weird thing to consider. Because if you have something like a gas, and you think and you're thinking about atoms in the gas, and say it's in a bottle, and these atoms are bouncing around, the gas inside the bottle has a pressure because those atoms are smacking into the container, and they're pressing out on it, right? And so that's your notion of pressure. And so you'd think that if you had a universe that was full of a bunch of tiny objects, call them geodes, and they're not smacking into each other, and they're not smacking into anything else, then how could a large collection of these things sort of have pressure? Right? They're not bouncing off of each other. They're not bouncing off of anything else. So like why should whatever's going on inside the geode influence what's going on outside the geode? And so people sort of thought that was the case. So it sort of agreed with this common intuition where you have like the sort of what I would call the kinetic theory, sort of conception of pressure. But that's not what you get when you do this sort of layered approach to Einstein's equations. You get that the behavior of the zero layer is complete average. Cuts right through everything. It sees everything. And so you pick up the pressures that are inside the geodes. And when you do that, things get wild. How am I doing? Are you guys with me?
I'm in. You're telling this story.
Okay.
It's wild. Okay.
Well, so we should definitely take a question break, though. So please, just sort of share with me where you're at, what you're thinking, before we go to the next step.
Yeah. So you've got these sources and the geodes, right?
Okay.
These things that they're out there. They're not pushing against each other according to this kinetic theory.
Right.
But now that you've done the math differently, looking at Einstein's theory, now you're going, no. They are influencing each other. They are doing something. They're influencing this stuff around them.
Yeah, that's right. That's what
How?
we got.
Why?
How? Oh man, you sounded like referees now. No, okay.
Wait a sec. Before how and why. Right before. So I was talking about this earlier about how gravity. We don't have a mechanism exactly for it. We can calculate how it operates throughout the universe, but we don't know exactly what a gravity stuff is. We don't know what the communication is. We don't know.
Okay, let's take it.
So we don't necessarily. I don't necessarily need to know what's the mechanics that are why a geode is a thing. But do we know, as we do with gravity, we can see its effects and how it is reaching beyond and having effects further than its locality?
So you want to so you'd like to move to the observational stuff, or would you like to?
I need an observation. I need a little observational.
Well, yeah. So I mean, the first thing that I would say, the first thing that drops out of the wash is that if you form a bunch of these geode objects around when the universe was maybe 800 million years old, you get what's called you get what looks like a cosmological constant that has the right value. So instead of just having to add some number to Einstein's equations, if this is the end stage of stellar collapse, if it doesn't form a black hole, but it instead forms these mu material objects, then you just automatically expect a cosmological constant. It's not like a weird thing. It just happens. Now, it's not exactly constant. There's some time variation. And if your observations are precise enough, you can tease out that time variation. It maybe shows up at about the 1%, 0.1% level. But there's a new experiment called DESI, a dark energy spectroscopic instrument, that is going to be able to look back pretty far. And they sort of look at galaxies in the sky and get very precise data as to how fast they're going away from us. And they might be able to sort of sniff the little effect that you would expect to see if you were sort of forming geodes instead of forming black holes. So that's one example of sort of how you just get the best fit model just sort of automatically when you have these things around, and yet you can distinguish it from the best fit model presently by more precise measurements. How do you feel about that?
Does that mean that there's a time point in the creation of the universe where it went from geode formation to black hole formation, or are they still completely separate phenomena?
No, so you could. So I guess they
could be the same.
Yeah, so you could. Yeah, you don't. So the position that I take, right, and it's maybe a position that I shouldn't take, but the position that I take is that you don't need black holes, right? They have all sorts of theoretical problems, and if you just replace them with these sort of dark energy objects, you just sort of start fixing other things that weren't making much sense before. And but if I'm going to be a straight scientist, which I should be, then they can coexist. There's no reason to have one or the other. And you have to apply like an Occam's razor argument to shave off the black holes. And so that's Blair, yeah, please.
Yeah, so I'm trying to synthesize all this. This is crazy. So I guess where I'm getting stuck is, does this change what we know, or does this change how we know what we know about the universe?
That's a pretty profound question. So I guess so. Let me just take a step back. I would say that this increases our confidence that Einstein's equations are very, very, very good description of whatever's going on. Because from the conclusion that we've conclusions that we've drawn working within Einstein's framework is that when you sort of start crossing T's and dotting some I's, you start explaining these phenomena that have been unexplained for a little while. And so that tells you that the currently accepted theory of what's going on for gravity is better than you thought it was, like much better than you thought it was. And so Einstein's got another home run. Yeah. And so that's I guess, does that answer your question?
Yeah, so it's kind of filling in these question marks in the equations that we were trying to use to explain things that we knew about the universe.
Right. So for instance, like the dark energy, you can add that. I keep saying it, and maybe I should have said it earlier. I'm sorry. You can model that. You can take Einstein's equations. You can just stick a constant in there, basically a constant times something called the metric. But you put basically a constant term in there, and it's permitted. You can do it. It doesn't break anything. But it seems sort of ad hoc, like you just pull it out of somewhere. And so a lot of people sort of had issue with that. Like they didn't think it was pretty, but other people were like, we don't care about whether it's pretty or not. It fits the data. It's the simplest model and we're going to go with it. Right. And so now you don't need to put that number in there, right? You can just, instead of forming black holes, which have problems of their own with the sort of one-way edges and the singularities that are on the inside, if you just get rid of that idea and you instead replace it with these dark energy objects, then you've solved those problems with one-way layers, and you've solved those problems with information paradoxes, and you've solved those problems with singularities. And you also get this cosmological constant number for free. So I would say that what we've worked on shows that, again, Einstein's equations are even better than we thought, like much better. But I think it also shows that we have a long way to go for really understanding or capturing the essence of what they're telling us. How was that?
Yeah.
Great.
Yeah.
So this idea originally, 50, 60 years ago was a thing. It was kind of not looked at for a long time. Geodes it's like, oh, geodes are out there, but not really looked at in the way that you've looked at them with your collaborators until
Right.
now. How is the astrophysics community responding to your ideas?
That's a great question. How am I going to respond to this one? So I have to say that, people are like, scientists are a pretty conservative group, right?
Yeah, very.
You really have to come correct. So you can't just like drop like I said, that first paper I pushed back in 2016 and they just threw it back at me. I was like, yeah, this is cool, but come on, do something.
Mm-hmm.
That's really the sentiment. And so the impetus when you've got a new sort of way of approaching an old problem is on you. You really have to make the convincing argument that people should pay attention to it. And that's just a slow process. First off, because, when you first come up with an idea and you make some connections, you don't have the fully clearest picture of what's going on. Like you can maybe sort of like the way we actually built the model, you don't see sort of you don't see all the puzzle pieces in their precision, right? You just sort of see, I'm looking at a puzzle. You realize you're looking at a puzzle and you're like, well, you start hunting for the border, right? And then you start laying the border pieces out. You find the corner pieces first. You get those corners in place. Then you start building off the corners and eventually you have a border in place. Once you get the border in place, you can start working your way in. And so that's really sort of how the research grows organically from this sort of initial idea to realizing like, okay, it's going to have these implications and moving on from that. So I can tell you that I had the fortune of having one of these sort of really prominent cosmology people just sort of down the hallway from me. And this guy's named Nick Kaiser, and he's no longer here at Hawaii. He's moved over to France. I don't want to say the name wrong because I don't speak French well. It's ENS is the abbreviation. And one of the most interesting things about working with a guy like that is that even if he doesn't agree with what you're saying, he can see all of the consequences of the idea very rapidly. And so I had this very like heated, dynamical, like exciting exchange with him where I'd be like, well, what about this? And he's like, I mean, I bet you could get the right cosmological constant if you made a bunch of these things, but that's crazy, and we'd iterate back at I'd be like, well, why is it crazy? And he'd, have some reasons. And then I'd take, okay, thank you. And, I'd go and sit and think about his reasons. yeah, do I agree with these reasons? Like, is it making sense to me, or does this not make sense to me? Or, do I, and sort of you continue this sort of like almost adversarial, but professional interaction with this person. And eventually you sort of like, you knock off the broken parts and you're left with the stuff that works. And I still think to this day, Nick Kaiser does not like what we're doing. but compared to 3 years ago, it's a lot tighter.
Yeah, I mean, that kind of that kind of relationship can really help your ideas, really, really hone them, fine tune them, and like you said, make them better over time. So we've got the geodes where we know that they're acting on things, they're on each other, on the stuff around them. So the papers, all three of them, you've now said that they, in your models, they support the idea of expansion, that they work in the way that we see the universe expanding.
Yeah. And so the thing there was that, so great. You basically did a counting game at that first level of the calculation. You did a counting game, smeared everything out and said, hey, can we get the right number? And you can pretty easily. It's very flexible, which is a nice thing to have. But if you that's not the universe we of course live in. We live in a universe where there's, not everything is identical everywhere. There's stuff. And it's distributed very unevenly. And sort of the thought was that, well, if you have a bunch of these very old geodes, just by virtue of what geodes do, they get much heavier since from when they're born to, say, the present day. And if you had a bunch of these things and they're really heavy, excuse me, and they moved around like matter does, you'd have a bunch of them hanging around galaxies. And that would destroy galaxies because they're huge. And they're like 10 to the 5. So I guess 100,000 suns-ish. That's a pretty heavy thing. So we've got about a bunch of things going around our own Milky Way galaxy that are of the order 10 to the 4. So 10,000 or 100,000. Yeah, 10,000. Mm-hmm. 10,000.
10,000.
10,000, not 100,000. 10,000 solar masses. And so they're usually called dwarf galaxies. So we got to think around, I hope I don't get the number wrong here, maybe around 128 of them, something like that. So there's this little like collection of little tiny galaxies going around ours. But you definitely couldn't have a population of 1,000, 100,000 solar mass objects. That would start causing trouble. And so it was very important that if this idea was going to be a viable explanation for this number that you find in Einstein's equations, when you look at the largest scales, that these things are not hanging around galaxies too much. And to answer that question, we had to take the first level calculation, use that as an input for the first level calculation. Did I say zero? Yeah, zero and then to first.
Zero to first. Yeah.
That's right. And we had to input that into the first, and then we had to see, okay, what's going to happen if we just sort of start with the very old universe when everything is still very hot and everything's still just sliding out and cooling down and nothing's really clumping together yet? Where do the geodes end up? And so that's the question we answered in the third paper. And it turns out that that their spin matters. And so if they're spinning very slowly, they clump faster than matter. They clump faster than black holes. And I understand this idea that that in terms of the geode themselves, I said they get heavier, right, as they get older. And so they get heavy.
Is that from matter accretion? I mean,
no, they get heavy intrinsically. And it's the same phenomenon that when you see light from a very distant galaxy and it's redder, that energy that's in the light is not because the galaxy has a relative motion to you in any sort of the Doppler sense effect. That's actually a common misconception. And you can run the math and see that it has nothing to do with the Doppler shift. What that is just the light losing energy because it's inhabiting what's called a Friedmann cosmology. It's not flat space. It's sort of a space that's filled with stuff everywhere. Mm-hmm. And the sort of end effect of there being stuff everywhere is that stuff sort of I don't want, for lack of a better word, entrains you or sort of saps you in some way, or usually saps you. And so for things
Life,
like,
it's like how I'm getting heavier over time.
but the thing is, no, like, but you're eating,
2020,
but you're eating
they're making me
right?
so
Like,
heavy.
You're bringing stuff in, so that's not the right
Yeah.
intuition.
Yeah.
And you got to be careful because there's sort of this old notion. It was called tired light in cosmology, and that's not the same phenomenon as the well understood photon redshift, which is what I'm talking about now. So geodes, instead of losing energy by virtue of their nature, so light loses energy by virtue of its nature, geodes gain energy by virtue of their nature. And so they gain energy pretty quickly, but geodes are not light, they're sort of localized things. And so when they gain energy, they gain mass. And so they get heavier. And so if you have sort of two objects, two geodes, or two, say, things that are not geodes, and they're rotating each other, as the universe is getting older and older, these things are staying the same weight, same mass. And so their orbit is not changing. But if you have two objects that are getting heavier as the universe is getting older, their mutual gravity is going to increase. And so they're going to spiral into each other. And in this sense, they collapse faster than regular matter does. And so we actually sort of characterized this effect in the second paper, but we didn't sort of consider the effects of spin. We didn't know how to do that at that time. And we only sort of considered what would be called the Newtonian limit. But when we did the third paper, then we had to sort of consider the objects in more generality. And it turns out that if they're not spinning, they clump real fast in that same way, and that becomes problematic. But if they're spinning, there's like a threshold spin, and then they start to repel each other. And lucky for us, it's expected that when matter does fall onto things like black holes, they spin up, because each little bit of matter also contains a little bit of spin with it. And when that falls into the black hole, it becomes integrated into the black hole. Remember, I said there's three numbers that characterize a black hole: mass, charge, and spin. And so you pick up the spin, and where's it going to go? It's going to make the whole thing go faster. And if you're pulling in tons and tons of matter, you're getting lots of spin. And so you can show that these things are expected to spin up pretty quickly. And so in that sense, we were able to make an argument that was at least good enough to pass the referee process at the Astrophysical Journal, that these things would spin up and they would undergo this repulsion effect. And so most of them would not be around galaxies. In fact, most of them would be distributed uniformly. But since most of space is these void regions, most of them are in voids.
Which we couldn't see anyway. So
yeah, they're
could be a
dark,
black
and they're
hole.
dark. And
They're
so
dark.
an object that's about 10 to the 5 solar masses, if it's almost the size of a black hole, is 1/4 the radius of the sun. And it's completely dark. So they're really hard to see. But there are signatures that you can pick up.
Yeah. Okay, so
Would
this
there be
gets to,
gravitational lensing?
is there going to be testing? Can we test this? That is the
Absolutely, right? And that's actually what's
step,
most
right?
useful about the geode scenario, is you can exclude it in tons of ways. It has signatures everywhere across so many scales, from the scale of compact coalescing binary systems to the scale of galaxies. You can count how many of these things might be around, to the scales of clusters of galaxies, and to the scales of cosmological distance. So we got two questions. One was from Justin, right? And then one was also from you, Kiki. So which, Justin, please remind me your question, or Kiki, remind me your question.
I mean, they're tiny, so it'd be hard to spot one. But
so you asked the lensing.
Gravitational lensing.
Yeah. So I don't think the number of densities, and I'm not an expert in gravitational lensing, I don't think the number of densities are sufficient for you to get sort of a strong lensing signal, like as to see something as like a blip. I don't think there's enough of that. And because they're uniformly distributed-ish, I don't think you'd be seeing a weak lensing signature either. And so that's sort of this. I don't know if you guys know what weak lensing is, but it's sort of when you look at some region of space and you look at a background field of galaxies that are further away than the region that you're sort of interrogating, and you look for subtle distortions in the orientations of the way those galaxies are. You'd think that normally, if you're looking at that region and there were sort of no shenanigans happening in between me and what I'm seeing, that all of the galaxies would sort of be randomly arranged right? Maybe they're ellipses and they're sort of randomly rotated ellipses, and there's no sort of preference anywhere. And so you start with that assumption, and then you look at some region of space and you say, aha, I see all these galaxies sort of stretched and squished and rotated sort of
something
subtly.
big in between us.
Something's in between us. Yeah. So something is sort of subtly affecting the background field. And if you can look at enough of these background field galaxies, you can reconstruct sort of what is sitting in between you and the background field. And so that's called weak gravitational lensing. And if you have these things sort of distributed uniformly, though, then you're not really going to have any preferential shears or deformations in one region or another region. And so I think the weak lensing signal would be small. Now, actually, this Nick Kaiser guy that I mentioned before, his bread and butter is weak lensing. So he might have some things to say about that. But I think I got it.
In terms of other tests, though, I mean, so, you could test light traveling through void regions of space, see how weak lensing occurs, whether or not it does. You could, is there other triangulation? Are there other
ways to get it?
Yeah.
So what you just said, actually, if you say we can look through light passing through voids, and if you just don't say the lensing part, you actually identified exactly the other way to look for these things. And that's something called the integrated Sachs-Wolf effect, or ISW effect for short. And so what happens there is that, or the usual way that it's described, is you have light sort of comes into a galaxy cluster, something very heavy. And as that light is coming into the cluster, it picks up energy from gravitation. And so it becomes bluer. And then as it leaves the galaxy cluster, it loses energy and it becomes redder again. And usually you would expect this effect to balance. So the amount of energy you picked up coming in is going to be equal to the amount of energy you lose going out. Right. And so you don't expect an ISW signal. But depending on how the universe is growing, if the universe is growing very quickly, like an accelerated expansion, then sort of the cluster itself is thought to get stretched with the expansion a little bit.
Oh, interesting.
And so the light coming in picks up energy, but as it's leaving, things got stretched a little bit too much. And so it doesn't lose as much energy on the way out. And so you expect that the light gets a slight blue shift. It gets a little more energetic. And people have looked for this effect, and they found it. So you can look in clusters, and you can use the light from the cosmic microwave background as sort of the backlight, and you can look for the imprints of structure on the cosmic microwave background. And you can look for these subtle shifts, hotter and colder. So you get the hotter ones when you have material. Likewise, if you have a very empty region, the same thing happens in reverse, and you get a colder photon coming out. And so it turns out that that geodes add a new contribution to the ISW effect, something called anisotropic stress. And don't ask me where that word comes from or what it means. No, you can ask me what it means. I don't know where the word comes from. It's just, to me, it's a very sort of confusing word. It's a sort of a characterization of the notion of things wanting to shear. So that's sort of like stretching, squishing, deformation. Mm-hmm. And so geodes add a source of this type of stress, and that changes the ISW signal. And so in the process of writing paper 3, we did a bunch of the simulations and have the results, and we still need to analyze them to compute the ISW effect to see, is it visible? Is it a large one? It could be too large, right? It could break things. People have measured this, right? And so we have to figure that out, make the measurement, and see if it's consistent with the data that we have already.
That's great. So you're working on the model. You've already got observational data. You're correlating things with, and so it's a matter now of just going through all of the possible places you can look.
Yeah.
Where do the geodes? What assumptions do you make, and what predictions can you make, and then how does that line up with your data?
Right. So we knew that from these binary star pairs in the Milky Way that they couldn't be hanging around galaxies, and so we had to get them away from galaxies. So it turns out that they like to get away from galaxies on their own, so that's good. if you're worried about binary star pairs and galaxies. But now they're sitting in voids. And so now we got to make sure that the data from the voids still makes sense. So that's next on the list.
All right. That's a lot. I mean, that's exciting. It's really, it's got to feel, I mean, how does it feel? You've got this new idea, this thing. I mean, it's not new, but
how
it's.
Does it feel?
Not really.
No.
Job
It's
security to me. Right?
Honestly, no, it doesn't
I
actually.
mean, do you feel like you're at the beginning of a journey, or is this?
And honestly, if I were to be completely honest, it feels terrifying. It's really what it feels like. Because, like I said, the community is a very conservative community, and if you really want to get people to pay attention, because to really investigate an idea, to consider whether or not someone's work, someone's analysis is correct, right? It's very technical stuff. It takes a lot of time. You have to be like, I care about this enough to really dedicate 2, 3, 4 hours a day, maybe for a couple of weeks, to get your head into the right space, to be able to understand, okay, what were they doing? Why did they go about doing this? And do I agree with their methods? Do I agree with their conclusions? And that's really hard work, and people are very busy. So there's a really, really high bar in order to get people to pay attention. And so I think it's just a very slow process. And so we're doing the best that we can to make connections with observations on many different scales that already exist and make predictions for upcoming experiments. And I think it's just a matter of time. It's a new idea, and people, I think, will be uncomfortable with it for a while. But if enough people begin to sort of notice that, hey, it keeps working, I think eventually it will sort of draw the necessary sort of harsh critical attention that it really needs to take it to the next level, right? You really need people that are going to come around and be like, I hate this and I'm going to get rid of it, you know? And then they come at it. Yeah, they come at it, right? And then they give you all that they got. And then, you know, if it survives, then it's like the 36 chambers, right? You got to start at chamber 1, and then you got to get to chamber 2, and don't try to go to chamber 35 first, because they're just going to push you out the door.
Yeah, don't go too far ahead of yourself. But I think you're already, you're already beyond just theoretical analysis. This is actually getting into experimental aspects. I mean, you're doing observational experiments, but this is experimental.
And I think what's one of the, I'm gonna give a shout out here to my department here in Hawaii, is that I had the fortune of sort of coming of age in an extremely observational and an extremely experimental community. So we have the observational astro community up at the Institute for Astronomy, and we've got a bunch of people that work on particle physics experiments here in physics and astronomy. And so whenever I would interact with my mentors here, the question was always, what are the predictions? How do we measure this? Yeah. You know, so I wasn't ever sort of allowed to get lost in theory land. I always was being pulled back and be like, all right, it's going to do this, or it's not going to do this. Am I going to see it here? And that was the way to sort of make progress with people, was you got to connect to the data. So that's sort of the approach that I think we've taken from the very beginning, was, all right, how do we best connect with the data? And because this idea is wild, the consequences are wild, even though we're working entirely within Einstein's framework. And people are going to have a pretty difficult time with this unless we can really show that it pays dividends. And so that's why we've taken the tack that we have.
I don't know why I got this funny image of what you've just described as a small bird continuously being pushed out of the nest, occasionally hitting and then having to come back to the nest.
Climb back up.
All right, I got it this time. All right, wait. Hang on. Heading back up.
I mean, I feel that sort of aptly describes the graduate student experience. You know, you're trying to fly on your own, and you're really not strong enough yet. But it sounds like they're having that focus of it's not just a nice idea that you can work on in the sandbox, but being pushed up against actual observation, experimental minded people must have accelerated your appreciation for the idea as well. Oh yeah, so I mean, there was a lot of, like I said, honestly a lot of fear, right? Like this, because the way that I came at the problem, it seemed to me to be sort of clear that there was only one way forward, but that was not at all what anyone else was doing. And so I'm like, am I just crazy? Like why doesn't anyone else seem to see this? Or like, why doesn't anyone approach the problem in this way?
And usually when that happens to me, it's because I'm wrong.
Yeah.
I mean, usually when that happens to me, it's also because I'm wrong, right? So, I mean, right. So this one's still going.
It's ongoing. It's really an interesting concept. And I think it's an interesting one to talk about because it really gives a new spin on black holes. And I
don't think I like Blair approved of that one.
I heard the groan from the stage. When the groan comes from the stage, that's when you know you're in trouble.
That's when you know you're doing your puns right.
Groan of approval.
Yes, I knew that. So there's a question in the chat room. This is it goes back to, I think, first order concepts, and I just have to ask the question. You talked about the supernovas and things that we're using to measure redshift and expansion in our universe. The question from the chat room is, I was told that no one has proven the universe is expanding as there was no direct measurement. I've yet to see a direct measurement. I've seen lots of proofs which assume the redshift is based on expansion, but I've never seen proof that it actually exists. How can you prove the expansion of the universe while you are confined to a gravitational well?
Okay, so I think the first way to answer this question is to sort of clarify that when you do physics or any sort of experimental science or observational like astronomy, you really don't prove anything. Like, proof is a concept that's squarely mathematical. You sort of lay out your assumptions, you lay out your axioms if you're really going back to the basics. And then you sort of follow a very strict logical framework to arrive at a conclusion. And that conclusion is called a proof of whatever concept you assert. So you asserted something and you're going to say, I'm going to show that given the assumptions I made, given the axioms I took, given the framework that I'm assuming for my logic, that I can string these things together and I can arrive at a conclusion. And then I will have proved this conclusion. So whenever you're doing stuff like observationally, you're never going to have that. You just can't get it, right? All you can do is sort of come up with a mathematical model with some sort of description of what you think reality should be doing. And then be like, when I look at the night sky, is this what I see? Is what I see consistent? And so you can check consistency. And so when we do that, we assume the model that Einstein wrote down is a good one. And we assume that because it's been very, very, very consistent with everything we've observed since its inception. And every new observation seems to strengthen this thing is working. Every new observation is consistent with the predictions of the theory. And the predictions of Einstein's theory tell you that light should redshift in an expanding universe. And it should redshift by an amount that's consistent with what we see. And so everything we do is within this framework of Einstein's theory. And if we were to suddenly find that something was not working, like badly not working, then we would be forced to sort of consider a different model. But the photon redshift is something that is very consistent, sort of consistent at a very low level. And so it's one that we have a very strong belief in. And I guess I will use the word belief here because it does come down to that. It is a belief in the validity or applicability of the model that we've chosen to work with. And so ultimately science does have to pick a model and choose to work on that. And at some point there will be enough data around and the data will be of sufficient precision that you'll see that model might not be the best way to go anymore. And then you build a new model. But until then, you work within the model until you find good reason to leave it. So in that sense, I would say that the photon redshift is real and confirmed, and it's consistent with and the distances that we infer from that effect make sense or need to be taken seriously. I think maybe is the way to say that.
And also that framework within which you're working has been challenged.
General relativity
has been challenged and tested, and My goodness, anybody who could find
Keeps working.
it just keeps working. And this is
it just keeps working.
It's actually
Yeah,
fun. I mean, that's probably the biggest surprise in all of scientific history is
Standard
how,
model, general relativity. It's like it works.
But general relativity has been around longer than standard model, so I'm gonna push my topic right here. You know,
okay,
we've been cruising for 50 years longer,
and it's just that's like the most mind blowing thing to me is that something that can start with a set of equations and observations in a human mind can then have thousands of human minds attack it from every angle and still find it consistent with the universe that we're in. Phenomenal mind. That's the most mind-blowing thing to me about all of it. But yeah, so it isn't
reality at this point.
And it isn't a dedication necessarily to that framework. It's been a framework people have really earnestly worked hard to
yeah, it's sort of like a dedication to knock it down. Yeah. That's right. And so
which reminds me of you earlier saying, like, I'm just waiting for you, just excited about the idea that your concept comes to the level in which it can be harshly criticized. So you're looking for that teardown to help knock off more of the parts that don't work and to bring it into a greater resolution, because that's one of the things that improves our concept of the universe is trying to knock down the assumptions or the assumptions based on evidence even that we have is by getting another attack from a different angle and finding whether or not it remains consistent.
Yep.
I can't wait until we're intergalactic travelers and doing these experiments to check and see if they still work then. You know, it's like, oh, yeah, when we can travel through wormholes.
I'll still be here.
Okay, wormholes. Do they exist with geodes?
No. So wormholes are an extremely interesting thing, actually. I have no idea. I have no idea at all. They're possible within Einstein's theory. You can build wormhole structures. Like they're consistent with the math. You have to sort of, as far as I know, you have to break something called the deck. You have to break the dominant energy condition.
Okay, the deck.
Yeah. Woo! All right, so reset there. You have to break the dominant energy condition to be able to hold a wormhole open.
Okay.
And the question is like, okay, you can do that, but when you break the dominant energy condition, what happens is there exist observers that don't agree on the causal ordering of events. So when the dominant energy condition is maintained, that means anybody, whether it's people like us or whether you're traveling with a light beam, everybody agrees on the same ordering of the way the universe plays out. Now, we won't agree on the time. We'll see certain things happen more quickly or more slowly, but the order of the events is preserved for everybody. If you violate the dominant energy condition, that is no longer true. And so people usually think that violations of the dominant energy condition are pretty bad news and should be avoided. But there's nothing intrinsic to Einstein's equations that says you're not allowed to break the dominant energy condition. And there's even situations in quantum mechanical systems where it appears the dominant energy condition is violated. And so it's really not clear whether or not a structure like a wormhole is a viable thing. As far as Einstein's equations go, you can do it. It feels a little naughty, but you can do it. Want to make the call back to the dominant energy condition here.
Yes.
And but quantum mechanics already seems to sort of suggest that there might be phenomenon like this. But that's sort of everything else is a theoretical game at this point with respect to wormholes.
So it sounds like there's a chance. So that's good.
Right. There's a chance.
So there's a chance. All right. Okay. So geodes don't break wormholes.
As far as I know.
Yet.
Yeah.
Okay, yet. Okay, good. All right. Thank you so much for sharing all of this information with us and joining us tonight. This has just been
very generous with your time.
Yeah.
Well,
it's
thank you.
been
I mean, thank
just
you for listening
wonderful.
to me ramble forever.
Oh, no, awesome.
It's been great talking with you. Is there a place that people can find more information about the work that you do, or?
So the thing is, there is like a Wikipedia page, but I'm like maximally conflict of interest, so I don't edit it. I've commented on the talk page about it, and just to sort of clarify some things for the editors to sort of decide whether it meets notability criteria yet and things like that. And so I would honestly say that the page is out of date, and it's not had sort of an expert's touch to make sure that things are correct,
Accurate. Yeah.
right? So, and maybe you're pointing the way that I really should just sit down and write some of this stuff up in maybe a more accessible way and just stick it on my webpage or something. If you think there would be interest in that, there is sort of there's a Stack Exchange, Astronomy Stack Exchange thread, sort of what are geodes, where someone asked and some astronomer was like, I never heard of these things. And so I actually got on there and was like, hey, I'm the guy that lead author of these papers, like, here's what's going on. And I answered their questions, and people were pretty satisfied with the responses, but they were a little technical. Is there a place? Not yet, but maybe there should be.
Yes, there should be. There should be a place where people can find more information.
So maybe you guys can edit the Wikipedia page.
Make
Bring
a
it up to date.
Twitter account.
Do I have it? Do I have a Twitter?
Yeah, you should
No.
make a Geode Twitter account and like
Social media terrifies me.
as Geode.
That's probably good. Don't get in. Just stay away. It's an evil, dark place right now. It's like the Hellmount.
It's a time
Awful.
suck for sure.
Yeah. No, it's terrible. We have a link to your webpage at the University of Hawai'i, and we can also link to the Geode Wikipedia entry.
So what it might be
on our
a little
website to send
technically
people that.
better if we link your podcast or we link this live stream. So just like put like a what are geodes? You just click it and it takes you to this conversation.
go.
If you think this conversation was useful,
It'll be recursive.
then, yeah, we can sort of drive the click traffic. You know?
Right. I like it. I like this idea.
You guys could make some geode merch. I don't know.
It's dark. Nobody can actually see
Yeah, I
it.
was gonna say.
It's there. Trust us. It's there.
Yeah.
I'm opening up the box. There's nothing there. Oh, it's there.
It's there.
I can send you a paper.
The hat is really heavy.
It's really heavy and it tries to push you away.
Yeah, stay away.
Stay away. All right, everybody. We have come to the end of our interview. Dr. Croker, thank you so much for joining us. We are going to continue on. You're welcome. We are going to continue on to some more science stories. You're welcome to join us, or
I think I have to duck out at this point.
Yeah, to go your way. Thank you so much for your time.
Thank you so much. Yeah.
See you guys later.
Have a good night. Bye.
Bye-bye.
Bye. All right. Thank you. This is This Week in Science. Thank you for listening. We are really glad that you're here with us. We hope that you learned something in that interview. I know I did. We try to bring you interesting interviews and conversation around science stories every single week, right? Down to earth, up to date views, credible, reliable, sane. That's what we really try to do. But it's all because of you that we're able to do it. So if you are able, head over to TWIS.org, click on the Patreon link, and choose your level of support to help us keep bringing this science sanity to the world and to more people. It's all because of you. We really can't do this without you. Thank you for your support. And we're back with more This Week in Science. And you know that interview, we went on and on and on about the astrophysics. So I think it's time for some Blair's Animal Corner. With Blair.
Doves are creatures great and small. Biped, millipede, no pet at all.
want to hear about animals, she's your girl. Except for giant pandas and squirrels, those animals for her.
What you got,
What you
Blair?
got, Blair?
Oh, yeah, there we go. It's like,
There we go.
I'm here. So I have a couple of kind of silly but fun stories that actually have some good implications to the greater scientific world. This one's
Bring it.
from Duke University. They love their primates. And this is looking at male baboons, actually 35 years of data, looking at more than 540 baboons over those 35 years in a national park in Kenya. Looking at platonic relationships. So relationships between males and females that are not related to copulation or reproduction. Because, there's been lots of studies done about family groups, about definitely female-female relationships, male-male relationships. But when we think about males being friendly with females, you tend to assume, as a lot of biologists would assume, that it has to do with reproductive perks in some way. Even if you're not currently getting any of those perks, perhaps you're hoping you will at some point. Maybe that's happening because they're related in some way to offspring, so they're helping protect. Or maybe that by giving kind of social behavior, friendly behavior, there's a hope that at some point down the line, maybe you'll get a shot. But then at the same time, we also know from studies with humans that humans who have close friendships are more likely to live longer than those who don't. And human studies also show that making and keeping friends can be as important for longevity as losing weight or getting exercise. So we have these two kind of very different ways of looking at the world. Perhaps no coincidence that one is looking at non-human primates and one is looking at human primates. And we are kind of want to separate from the it's all about sex thing. Like, no, you can be friends with a guy
too. Yeah.
Fine. But then when we're looking at the baboons, we don't want to believe that for some reason, which I think is maybe it's a subconscious thing. I don't know. Anyway,
I'm fine with it.
there's been these patterns of opposite sex friendship that has been seen all over the animal kingdom, but especially a lot in mammals. And they use statistical techniques to look at mortality risk at each age and to see if there was links between survival and friendship, and if those were the same for males and females. They do spend a lot of time together grooming, which is usually how you look at social behavior in primates. That's how they bond, that's how they relieve stress, and that they help each other with hygiene. And there's this push-pull. I help you remove those bugs, you help me remove my bugs, right? Males don't spend very much time grooming each other. Makes sense. They're probably rivals. They don't want to help each other. But they do groom with females, even ones who are not currently fertile, who are currently with a child from a different individual. So they do it not just right when it might result in sex. So they looked at 277 males, 265 females. They looked at the strength of the bonds in their inner circle, basically just by the time grooming each other. And they found that both sexes have benefit from strong social ties. And the males specifically live longer lives if they're socially connected. And that males that maintain strong female friendships were 28% more likely to make it to their next birthday than ones that were socially isolated. That's a very dramatic way of putting it. But so it has it's a strong indicator. So of course, more work needs to be done to look at how those links have. Is it causal? Is it correlative? And then if it is causal, how do those bonds specifically affect physiology and lengthen lifespans? Is there a physiological change? Is it all hormonal or mental? So these are all questions, right? And so this is bringing it way back, saying that it does seem like friendship has evolutionary roots very far down, definitely in the primate family tree, probably in the mammalian family tree. I bet you could go further. But yeah, I immediately think about stress.
Mm-hmm.
That an animal group that's not a solitary one their stress hormones will be reduced if they are having physical contact with other individuals, whether or not they're getting reproduction out of it.
And I would imagine it also helps strengthen the bonds within the social group as a whole, so they've got their little band of baboons, that their troop that they rely on. And if you are involved in a mutual grooming relationship, a friendship with other individuals, you're going to be able to rely on those individuals. Is there a food shortage? Is something dangerous? Is something happening? There is that undercurrent of troop trust that I think and that also goes back to stress. It probably would reduce stress. It maintains those bonds. And I would imagine it probably allows everyone to be cool.
Yeah.
And live together.
Absolutely. Yeah.
Except
So
that we're
will
talking about
astronauts-
baboons.
Yeah, but
Yeah.
I know, very
I feel
violent
baboons
animals.
are,
Yeah.
Yeah.
I feel like that's a stress-based society.
Right.
So,
if you
will
could reduce some,
astronauts mutually groom when we're on
Oh.
Mars?
yeah, they should.
Oh.
It also, I was never a girly girl growing up. I didn't really have any female friends. And then I got to college and I joined a sorority, and suddenly I had all these female friends. And the
That
first
happens.
time I had another girl braid my hair or like mess with my hair, thinking back on it with like the science hat on, it could only be just a rush of positive hormones, just like a flood of dopamine or something. I don't know, but it feels really good, and it just feels like you're being like taken care of in a space that you can't see. And I don't know, it's really hard for me to describe, but it is, when girls braid each other's hair, there's a reason for that. I would guess it has something to do with this, but yeah, it's
Bonding.
interesting to think about it from the baboons, but also with humans, especially in COVID times when we're not allowed to touch each other.
I think I
Yeah.
experienced something very similar to that with a significant other who basically pinned me down and clipped my nose hair.
No.
No.
I don't want to do it. I don't want to do it. Just stay still. Stay still. This has to be done.
No.
You definitely have to
don't
trust
poke
the
me.
person with the
Previous or
scissors.
current?
This is
I'm very
current.
curious.
Very
Okay.
current.
Okay, current. Good. I was hoping. It sounded like
Yeah.
that was the right MO. Anyway, moving on from reducing stress to fear. Pretty simple story. Just looking at this is from the Institute of Marine Biodiversity Exploitation and Conservation, looking at the impact of humans on how wild animals respond to predators. And sometimes it takes a little bit of science being done to confirm what I'm sure we all would have guessed, which is the more animals come into contact with humans, that could be through captivity, domestication, or urbanization, they stop avoiding predators. Their avoidance behaviors like vigilance, freezing, and fleeing, they all start to deteriorate. They analyzed results from 173 peer-reviewed studies. They looked at anti-predator traits, both behavioral and physiological. So they were looking at long-term evolutionary changes as well. In 102 species, they looked at domestic, captive, and urbanized mammals, birds, reptiles, fish, and mollusks. So this is a pretty big swath of life that we're looking at here in terms of animals. And they found that contact with human overall led to a loss of anti-predator traits. And simultaneously, the variability between individuals increases and then decreases in generations in contact with the human. So basically, the human comes in, reduces pressure from natural selection because they're kind of letting everybody survive. And then think about like dog breeds, right? Some of them that are spent their whole lives in the doctor's office because of traits that were allowed to continue that could have been a problem, right? So they reduce pressure, so that allows them to kind of radiate. And then after that, then they've kind of started to be selected for being more docile or domesticated. So they had almost immediate changes in responses in the first generation after contact with humans. So the initial response is all behavioral, and then genetic changes come later on, of course. So domesticated animals, their anti-predator responses started to disappear 3 times faster than urbanized animals. So that makes sense. You're talking about a dog versus a pigeon. So definitely animals that live in your home, are domesticated, are cattle, things like that, they are being selected for, and they are dependent on humans to survive. Urbanized animals are not being intentionally selected for by humans, and they also use humans to help them survive, but could survive without them. So it's kind of a different thing. And then captivity actually had the slowest changes, which is great because that's where endangered species are being bred to be released into the wild. So this is actually great news. Also, herbivores apparently change behavior more quickly than carnivores, and solitary species change quicker than group-loving animals. Yeah, so the solitary versus group-loving, that should jive because group-living animals have versions of themselves to gauge how they act. But if you take a solitary species and you bring them home, they think they are you. They don't have another version of them to
compare to.
They think
Right.
they're one of whatever they're around. So that would make sense. So obviously
I don't think my cats think that they are me, though.
Right, but
No.
that might be
No, but they think
two
that
of them.
they think that they're the humans in charge of your household.
Yes.
Is what they
Right.
think.
Right, exactly. Yeah, there's a hierarchy, but they might think
Mhm.
you're all the same species.
Yeah.
So obviously loss of anti-predator behaviors can be a huge problem because they don't run away and they get eaten.
Mhm.
And so there's a lot of implications for conservation, captive breeding programs, like I mentioned, livestock management. So this is an important study because I think the first thing that I took away was what I said, like, great, awesome, captive breeding is the lowest impact. So let's just keep trying to reduce as much of that impact as we can if we're trying to captive breed animals for later release into the wild. That's excellent. But this also is a reminder. I brought this because a few weeks ago, someone had asked about feeding wild animals on your porch. That is exactly what we are talking about here with urbanized animals. So if you get them used to humans, then they might get eaten. So so it really is that you want them to be a wild animal, do wild animal things, because that attributes to more than just their diet. It attributes to how they're going to react if they see a coyote or a mountain lion. So it's part of the overall survival of these animals is making sure that the only ones getting this intense, specified, selected contact by humans are species that we intend to live with us forever, hence domesticated species, right? So
That's cool. Yeah, it's interesting.
I want to ask a real quick question. Which one got the predator response reduced quicker? Was you were carnivore versus vegetarian?
The herbivores did it.
Herbivores,
yeah,
reduced faster. Okay.
Yeah.
Okay.
Yeah, they got their guard down quicker.
It's just interesting.
Yeah, because
that is interesting. You'd think
it made me think of sharks being terrified when there's orca present. Because I think if you are a predator, another predator must be terrifying because it's not your maybe it's not your normal mode of approaching the world. You're looking at the world like it's your food. Whereas if you're an herbivore, other animals might seem more like they're looking at you like your food. So
there's another piece that I'll just throw out there, and it's something that animal lovers don't often like to talk about, but a lot of carnivores eat their own.
Yep.
So I think that's part of it too, is if you have, no matter how much humans are taking care of you, if you're a polar bear, you still have to watch out about being eaten by other polar bears.
Polar bears. Yeah.
Yep.
So that, I think that's kind of like the big secret about those
of the
charismatic
captivity?
megafaunas.
They'll eat you. They'll eat each other.
They'll eat each other because meat is meat.
Yep.
So it's,
It's an interesting thought. Ah, fascinating. Hey, Justin, did you have any stories?
Oh, yeah. I actually do somewhere. Okay, yeah. This is from Forrest Stewart, who is an associate professor of sociology in Stanford School of Humanities and Sciences. He worked with some researchers at the University of Chicago, Kaylee White and Shannon Morrissey. They were looking at how Chicago news organizations cover homicide victims in the print. And they focused on Chicago in 2016, which was one of the deadliest years in the nation's third largest city. They had 762 people who were homicided, murdered. Not fun fact, Chicago has a serious homicide problem. And sort of like looking at some of the sources of where this data was collected, it's pretty grim. But that's just the not fun fact. So this study was just published in the journal Sociology of Race and Ethnicity. What they basically did was they looked at how people are written up after they have died, after they have been murdered, in the little blurbs of the local newspapers. And they found a disparity in how people were written up based on race. So they... So here's the disparities extended to the city's Hispanic majority neighborhoods and Black majority neighborhoods versus the white majority neighborhoods. Chicago is sort of an interesting place because it is basically, it's a third African American, a third Hispanic, and a third Caucasian. You would think this would be a very sort of place that you would have this blended pool of being able to see a sort of maybe a uniform approach. However, despite the makeup of the city, it is still a very segregated city. There are vast majority of Black, vast majority white neighborhoods, vast majority Hispanic neighborhoods as well. So despite its diversity, Chicago remains a very segregated community. Basically, this was something that Stewart had come about because he had sort of been looking at, there was Jacob Blake, his sister said something interesting in an interview when she said, and when you say the name Jacob Blake, make sure you say father, make sure you say cousin, make sure you say son, make sure you say uncle, in an effort to humanize and not allow that attack to be a statistic.
Yeah.
And so he sort of got interested in this and started looking into how press covers these things. Is there something that you can quantify? So quoting Stewart here, as a social scientist, I thought, wouldn't it be even more powerful to quantify the value of different folks' lives from different racial identities and backgrounds in news coverage and hold those up next to each other? So this is how he came about focusing in then on Chicago, which has a few databases that list everyone who has been murdered in their city, and has a couple of places where they actually have then links to where this has been reported in the news. They examined 2,245 news articles about homicide victims. They looked at how much coverage each person received, considering factors like word count, and which articles recognized someone as more than a named victim, but as a complex, multidimensional human being, mentioning family, community connections. There were articles, some of them where they did interviews with other people in that person's life. They cross-referenced these also with Chicago Police Department public records. Their analysis determined that about 35% of murder victims in majority white neighborhoods were likely to be covered as a complex person. That is double the amount in majority black neighborhoods, which was 17%, and Hispanic neighborhoods, which was 18%. Homicide victims in majority white neighborhoods received about 450 words more of text on average than those killed in majority black neighborhoods. Researchers found that black victims' names were sometimes misspelled, had transposed letters in the news reports. Even just reading the news articles, this is Morrissey, who's out of Chicago, even just reading the news articles, there was a palpable difference in the way victims and neighborhoods were talked about. This paper does well to remind us that the disparities are on a neighborhood and community level. So they differentiated between articles that simply listed a victim in a weekend review of the homicides and more nuanced articles that tried to capture an individual's lives. There were other articles, especially about victims from majority white neighborhoods, where the reporters were doing interviews with family members and friends, with teachers, coaches, all sorts of people in the victim's life, and they were providing quotes, said White, who's Department of Sociology, University of Chicago. They talked about the victim in a very different way, like this complex person who has value and who's being missed by the community, family members, and friends. So Stewart, at the end is saying here, race isn't just your phenotypical coloring. Race is a series of historic, economic, symbolic, and importantly, geographical set of power relations where some people are stigmatized and rendered powerless or less powerful. These are systems of domination. Mm-hmm. So even, when we have had these conversations about what is systematic racism, what is an institutional racism look like, here's a pretty good example. Just the way that the community is reporting on the victims of homicide has a racial bias to it.
Has a huge bias. And I think there are many examples. There have been people within media who have often said, make sure you look at the verbs, at how the headlines of stories are even worded, because the way that they're either passive or active voice, the headlines are worded in a way that make you immediately emotionally jump to a certain conclusion. And then like all these bits of evidence that you've brought in through this story, it's part of that systemic disenfranchisement, telling a different story.
Mm-hmm.
Yeah, there was a really interesting article actually from NPR back in June about how Black victims are usually called unarmed Black men specifically, is part of the phrase, which it actually has an implied bias saying that young Black men are expected to be armed and dangerous. And so there's actually something that NPR wasn't even aware of, and they had to be educated, and they had to release this article and say that they were going to change the way that they did this, because if a victim is white, they're not called an unarmed white person.
Yeah.
So it's there's definitely something there that sometimes it's so baked in that even trying to be just the most impartial, inclusive, it's still there.
Yeah, no, that's a fascinating one. That was never occurred to me. But yeah, unarmed Black man, we've heard this phraseology over
so many times,
especially in a lot of these reports. But yeah, you don't hear about the
which at first you start to think like, oh, they're actually indicating that they're
pointing out the fact that
innocent, right?
This was an innocent. But by that, this was an innocent Black man because they were not armed, as would have been, then it would have been acceptable.
Right. Or the implication that is somehow an outlier from the expectation.
Yes.
Right. Yeah, totally.
100%.
Our words matter. And I think the point with this particular study is really interesting, that Chicago, you would think since it is fairly evenly divided,
Diverse but not
racially,
integrated. Which
but
is
not
the sort of-
integrated. That's the big kicker kind of there. But
Well, the
you
other
would
thing
thi-
is that
yeah.
the
Can we
discipline
get
of
away from that
journalism,
language? Yeah.
the discipline of journalism, which is supposed to be impartial, is supposed to be in that active voice, and it's
Mm-hmm.
supposed to be telling the stories of the community. When you have the system that is designed to be unbiased in its recounting of events and things taking place, and then you find that layer of bias palpably, in the words of the researchers, obvious.
Yeah.
That's like the definition of an institutional or systemic racism or bias. That the journalists doing this, it's not like they're like, oh, I'm going to intentionally, specifically refer to this person the way they died because of their race differently than it. And it's that hidden bias that is even worse in a way, because that way it continues without even the person authoring it necessarily recognizing that it's taking place. So hopefully, that now this has been done in one city. It doesn't mean that Chicago is an outlier.
No. Yeah. I'm sure that if it were to be analyzed across the United States, we would find it everywhere. Unfortunately.
So hopefully this story gets some traction within the journalistic community, so that they start to pay attention to the way bias affects their reporting of events.
Yeah, that's a great point. This is This Week in Science. If you like this show, help us grow our audience. Tell a friend to subscribe today. I have a couple of stories before we finish our hour here. Let's talk about brains. Brains and how they develop. Yes. Shall we go there? Yes. Yes, we shall.
I love this story. Yes.
Yes. Let's talk about how brains develop. When you have a baby, you think, it starts out as a little ball of cells, that blastocyst, and the blastocyst then has all these cell types. It has its genomic map to be able to turn into all the different cell types that the body needs. There's gastrulation, and the body gets a gut, and then it starts dividing, and look, there's like a little head area and a tail area, and there's little limbs forming. And meanwhile, the shape of the body is taking shape. There are cells for the different tissues that are taking shape as well. Neurons start to grow that start connecting different parts of the body, the brain to the gut. The brain starts to form. But you often talk about the things that mothers eat while they are pregnant affecting the development of the offspring. We often talk about even the things that mothers have put in their bodies leading up to the pregnancy. Were they a drinker? Were they a smoker? Do they have enough folic acid? All these things that we know can potentially affect that young baby. Well, questions have arisen as to whether or not microbes have any impact into that brain development. And you might think, wait a minute, whose microbes? What? Because, we know there's the placental barrier, right? There's the placenta. It mingles the mom's blood supply with the baby's, but it's a barrier, kind of like the blood-brain barrier, and it's supposed to kind of let nutrients pass through, but it's this very specialized organ to support the growth of the baby. And so the nutrients come from the blood of the mother to feed the developing embryo. So how could microbes be involved? Why would they be involved? Well, some researchers just published a paper in Nature this week reporting that when they took microbes away from pregnant mice, started out with germ-free mice, no microbes, or mice that they gave antibiotics to, the offspring of those mothers, the brains did not develop in the same way as the mothers that had a normal microbial population. Did not develop the same way. So they had behavioral abnormalities. They responded to scary stimuli differently. And they also saw that the axons, the actual parts of the neurons that connect the neurons from one place to another, they were smaller, they were shorter, they were stunted. They were not growing to the extent that they should have. They didn't group in axonal bundles the way that they should have. And these groupings, it's called the internal capsule in the brain of mice in which they did these studies, were thinner than embryos from mothers that had a normal microbiome. Lots of genes that were expressed were different as well. So some of those genes were genes responsible for axonal development. When they put bacteria back in, probiotics, they were able to offset these neurodevelopmental abnormalities.
Oh, wow.
Yeah, so they did a bunch of different tests to find out, exactly how this was working, but the evidence that they have amassed in the large part suggests that there's something about metabolite molecules that get produced by the gut microbiome and that end up in the bloodstream. So it's not like microbes themselves are going into the babies to change their brain development, but there is a change to molecules that are important to nutrition. And those molecules then are also important to the development of a fetus.
So it's the microbes. Is it just basically then saying that without the right microbes, the mother doesn't get the nutrition that can be passed on to the kid? And then, so in this case, these are like malnourished mothers giving birth?
Yeah, but because the mothers are adults and they're doing fine, the mothers themselves, for all
I
for all
assumed it had
measures
to do
are
with
fine,
like hormones, like it always does. I know I'm always the one crying hormones. Is that like microbes affect hormones, right?
Yeah.
So that was kind of my assumption, is that the microbes are somehow impacting hormones that impact development.
So the question is, how do they affect development? We don't know. We know that there are what they're calling microbiota-derived metabolites. So they are little bits of proteins that end up in the bloodstream and they have effects. And so whether those effects are to trigger hormones or to trigger, or to, what do they trigger? What do they get involved with? We don't know necessarily.
Interesting.
Yeah. But the specific area of the brain that they did find to be most highly affected in the mice was the thalamocortical sensory relay pathways, particularly in neurons that are involved in heat, sound, and pressure detection. And so while it's a broad effect on the brain, there is this particular area of the brain that microbial metabolites seem to really have an effect on. And so the question now is, okay, we've seen this in mice. What is the, how does this change? Does it change in humans? What is the effect of maternal microbiotas in human pregnancy?
And
So
then
stop. Dr. Justin's not a Dr. Poo pill for super smart babies.
I was going to
Right.
suggest. I was just going to suggest. Yeah, the morning show headline is eating yogurt while pregnant going to give you a smarter baby. Science says yes.
But more so, it's not, is it going to give you a smarter baby? It's, is it going to affect abnormalities? So will we be able to track biomarkers, metabolites in the blood of mothers? Can you have like a little, instead of an insulin stick or whatever, can you have a little pinprick kind of thing or a saliva test that you do on a daily or weekly basis when you're pregnant to make sure that your levels of these biomarkers are fine? And if the levels of these biomarkers are low, then you know that you need to eat yogurt or whatever, whatever the probiotic, whatever it is.
That's great. That's very cool.
Yeah. Yeah. So there are definitely directions that this could go towards very beneficially affecting the developmental brain health of babies, which is super cool.
I think all the time about how there was a period of time when modern medicine was throw antibiotics at it. And then we kind of discovered like, ooh, maybe that's not a great idea. But now I'm kind of picturing the opposite now where it's throw bacteria at it.
Yeah, but and on the other side of that, Blair, while you're pregnant, if bacteria have such a big effect on brain development, antibiotics while you're pregnant, that is maybe that's a last ditch kind of thing. Like you only do that when you really can't get rid of something. I mean, what this implies is that that bacterial populations are very important for fetal development.
Yeah, or at least if you are going to do an antibiotic while pregnant, have a probiotic backup plan for regenerating after. Yeah,
exactly.
Just shotgun your cult on your way out of the doctor's office.
And that's where Dr. Justin's not a real doctor. Poo pills
come in
for whatever ails you.
That's right. Yeah, it's very, very exciting and definitely going to push forward on more research surrounding this because it's so interesting. My last story has to do with reality and how we really, really know what's real. Have you ever experienced kind of an out of body experience or a feeling of detachment from reality?
There's a way to attach to reality.
Just not feel connected to yourself or the things going on around you.
Is there a connection available?
Dissociative disorders are disorders that are common, resulting from trauma or abuse. Ketamine is a drug that can lead to dissociation, and dissociation can also occur in epilepsy. But dissociation is a known effect that happens, and we've never really known why it happens. We know that brain rhythms change. There's been a lot of work into these areas. But again, a new study in Nature describes a study that researchers did using a bunch of different drugs and looking at how the brains of mice responded to a bunch of different drugs. They looked at sedatives, anesthetics, hallucinogenic drugs, LSD. They looked at ketamine, phencyclidine, diazosillapine, drugs that induce dissociation on purpose. And they went digging around to see, using a technique called wide field calcium imaging to look for changes in frequency rates in brain rhythms. So what was the pulsing rhythm of the activation of neurons in various areas of the brain? And they found that all of the dissociative drugs made oscillations happen at about 1 to 3 hertz. So very low frequency, 1 to 3 hertz, in an area of the mouse brain called the retrosplenial cortex. And this is an area that's involved in episodic memory, being able to remember all the details of an event. Navigation is important for other cognitive functions also. And other drugs did not. So like LSD didn't trigger the retrosplenial cortex. No dissociation. Hallucination? Yes, but not. The retrosplenial cortex was not activated. So they were like, all right.
You're stuck with yourself, whether you like it or not.
Whether you like
it, covered in bugs, but you're right there.
You're right there, still in reality. So these researchers looked at the cells using what's called 2-photon imaging, and they found that the cells in the retrosplenial cortex were restricted to a really small area, or layer 5 of the retrosplenial cortex. Just only the cells in this little layer 5. And they saw the neural activity take place. Ketamine caused a disconnect from a number of different brain areas so that they didn't communicate with the cortex, the retrosplenial cortex anymore. However, they wanted to know whether the retrosplenial rhythm on its own by itself could cause that disconnect, that disassociation that ketamine caused. And so they used optogenetics. Is that what it is? Yes. Anyway, they used these two proteins that are sensitive to light and this channel rhodopsin. They got one neuron to respond to blue light, another neuron to respond to yellow light. The blue light turned the neurons on, yellow light turned them off. And so they alternated the neurons using light in this 3 hertz range. So they basically artificially, they pumped in blue and yellow light to the top of the mouse brain, beep, boop, beep, boop, beep, boop, beep, boop, turned it on and off and on and off. And lo and behold, they actually caused the dissociative effect in the brain of the mouse. They watched it happen. Then they're like, this is not enough. What about people? Can we do this in people? And so they tried this in people, stimulating a similar area of the brain. We don't have the retrosplenial cortex in our brain, but they were able to look at the deep posteromedial cortex, and in a person who has epilepsy, and they had electrodes already implanted in their brain. And so they stimulated those electrodes and were able to cause dissociation in the person using the same frequency. So the person was awake, because usually when they do these epilepsy experiments, the person's awake and responding to things. And so they could say, okay, we're going to turn on the electricity now. Let us know if anything happens. And then the person can say, whoa, I feel like I'm having an out-of-body experience. I feel really weird. And so the patient that they were able to experiment on in this 3 hertz rhythm, it worked. Wow. So, yeah. So the question is now, can we induce dissociative states in people more broadly? Would we want to?
Yeah, that's what I was going to ask. Why would we want to do that?
Well, one of the questions about ketamine, it's been found to have antidepressive effects and can be very helpful for other mental health reasons. And so without giving somebody a drug, could you actually stimulate these effects? Could you, instead of having somebody go to a clinic and take the drug on a monthly basis, which could be very difficult, maybe you could implant electrodes, kind of like a pacemaker, that would stimulate this effect on a regular basis and then have the antidepressant effects. This is just, hypothetical. The other question, though, that I think is really interesting is, why do we have an area of the brain that has evolved to associate our consciousness, our physical body, to like reality? Why do we have a part of the brain that if it does a certain activation, we have dissociation? Is it because we have to survive? We see dissociative effects because of trauma and other. Is this because we are a survival-based species? Has it evolved? I mean, but why do mice have something similar? Why do we as mammals have a part of the brain for dissociation?
I wonder if as the brain gets larger and you become more aware of what's going on around you and what is happening to you, right? You're getting more intelligent, which helps you survive, but it also means that you're more susceptible to trauma because you're more aware.
I kind of think that's the other way around. Wouldn't it be that this means that there's a part of the brain that's required for us to even associate ourselves with ourselves? Like that's its function. It's like that's not the natural state of things. You had to like have this workaround to associate the things that are going on with
you're
yourself.
saying there's an on switch
and my hand.
An off switch.
It's my
we
leg.
found it an off switch. It's not that that's built into to make us disassociate. That's how we even associate with ourselves in the first place. That's what it's doing. Without it, just sort of observers of this being going on.
Yeah, so I'd love to see more studies kind of looking at the the neuropsychiatric side of it, kind of Oliver Sacks style, of people who have had damage to that area of their brain, and how does that affect their ability to associate their body with themselves, to associate their surroundings with themselves. Yeah, I think I'd love to see that evidence.
I'm convinced that the brain's main function is to take all these disparate parts of an organism and make them function together.
Mhm.
The analogy I often use is that if your body didn't punish you, you wouldn't know to eat.
Right.
If you didn't, you wouldn't get hungry if your brain didn't be like, okay, negative response. You have to overcome it by doing this. That's how it controls this otherwise absolutely stupid, what would be brainless entity, and to survive, forcing this thing to survive. And yeah, forcing us to associate ourselves with ourselves is an important thing for an organism to be successful.
Yeah, and as Fada says in the chat room, an extension of this is also potentially the ability to have any sort of abstract thought beyond the present moment. Yeah. It's all very interesting. And yeah, is this part of the brain? Is that one part of the brain, the thing that ties us to reality? Is it? Very.
And it doesn't necessarily have to be a real reality. It just ties us to the reality that we assume is the one that we live.
The reality that we produce in our head. We are at the end of the show. Thank you for sticking with us. This has been a wonderfully fun and long show. And speaking of reality, final thoughts for this show. We don't have a question for the end of the show tonight. If you do have a question for us, please send me an email, kirsten@thisweekinscience.com, or leave a message on Facebook. But I just want to say that the world really does seem kind of crazy right now. And it's out of control. There's a lot of stuff going on. You feel like, I think Chuck Wendig put it really well in something he wrote this week, which is that you feel like you see there's a toilet on fire in the middle of the living room, and you just wonder if everybody else sees the same toilet on fire in the middle of the living room. And, I see that toilet on fire in the middle of the living room. I'm just telling you right now, the toilet is on fire, and you're not alone if you see it too. So just keep your wits about you, stay curious, and check your sources. Like Justin said at the beginning of the show, check your sources. And I do hope that you continue to count on us as credible and reliable sources of information, and also discussants of information. And that but if you see or hear something that we say, double check us, because that's what we hope that you do. Mm-hmm. We hope that we inspire you to be more curious and to look into things. But thank you for spending your time with us. And for the next week, stay safe, social distance, wear a mask, wash your hands, make sure you registered to vote, because that's coming as well.
And if you
and
can
get
do
a
it
flu
this
shot
week,
also.
And get a flu shot. Thank you for listening. I do hope you enjoyed the show. Shout outs to Fada for your help on the show with social media and show notes. Gord, thank you for manning the chat room. Identity 4, thank you for recording the show. And I'd like to thank our Patreon sponsors and the Burroughs Welcome Fund for their generous support of This Week in Science. Thank you to Jonathan Stylo, Jonathan Styles, a.k.a. Don Stylo, John Scioli, Guillaume, John Lee, Ali Coffin, Maddie Perrin, Gaurav Sharma, Josiah Zahner, Mike Shoemaker, Sarah Forfar, Donald Mundis, Gerald Sorrells, Stephen Alberon, Daryl Myshak, Stu Pollock, Andrew Swanson, Fred S104, Corinne Benton, Sky Luke, Paul Ronovich, Ben Bignell, Kevin Reardon, Noodles, Jack, Brian Carrington, Matt Bass, Joshua Fury, Shauna Nina Lamb, John McKee, Greg Riley, Mark Hessenflow, Gene Tellier, Steve Leisman, Ken Hayes, Howard Tan, Christopher Rappin, Richard, Brendan Minish, Melizond, Johnny Gridley, Flying Out, Richard Porter, Christopher Dreyer, Mark Mazzaros, RDM, Greg Briggs, John Atwood, Robert, Rudy Garcia, Dave Wilkinson, Rodney Lewis, Paul, Matt Sutter, Philip Shane, Kurt Larson, Craig Landon, Mountain Sloth, Jim Drapeau, Sarah Chavis, Alex Wilson, John Ratnaswamy, Stu Doster, Jason Olds, Dave Neighbor, Hosty Ranky, Matthew Litwin, Eric Knapp, EO, Kevin Parachan, Aaron Luthen, Steve DeBell, Bob Calder, Marjorie, Paul Stanton, Paul Disney, Patrick Pecoraro, Ben Rothig, Gary S., Ed Dyer, Tony Steele, Ulysses Adkins, Brian Condren, Jason Roberts, and Dave Friedel. Thank you for all of your support on This Week in Science. If you're interested, you can go to twist.org and click on the Patreon link and go to patreon.com/thisweekinscience. It takes you there. On next week's show, we're going to be talking about viruses and COVID-19 and heart disease with Dr. Efra Rivera Serrano.
We will. So yeah, then we better get back here next Wednesday, 8 p.m. Pacific time. We'll be broadcasting again live from our YouTube and Facebook channels and from twist.org/live.
Hey, do you want to listen to us as a podcast? I wouldn't suggest it. You'd miss all of the dog stuff happening on screen right now. But if you want to, go ahead and search for This Week in Science wherever podcasts are found. If you enjoyed the show, go ahead and send it to your friends. Tell them to subscribe. They'd love it.
For more information on anything you've heard here today, show notes and links to stories will be available on our website, www.twist.org, and you can also sign up for our newsletter.
You can also contact us directly. Email Kirsten at thisweekinscience.com, Justin at twistmeeting@gmail.com, or me, Blair, at blairbaz@twist.org. Just be sure to put TWIS, TWIS, in the subject line or your email. Well, it'll end up in, what did we decide? Not a black hole, but
a geode.
A geode.
You can also hit us up on the Twitter where we are at TWIS Science, at Dr. Kiki, at Jackson Fly, and at Blair's Menagerie. We love your feedback. If there's a topic you would like us to cover or address, a suggestion for an interview, a haiku that comes to you in the night, please let us know.
We'll be back here next week, and we hope you'll join us again for more great science news.
And if you've learned anything from the show, remember,
it's all in your head.
This Week in Science. This Week in Science. This Week in Science. This Week in Science, it's the end of the world. So I'm setting up shop, got my banner unfurled. It says the scientist is in, I'm gonna sell my advice. Show them how to stop the robots with a simple device. I'll reverse global warming with a wave of my hand. And all it'll cost you is a couple of grand. 'Cause this week's science is coming your way. So everybody listen to what I say. I use the scientific method for all that it's worth, and I'll broadcast my opinion all over the earth. 'Cause it's This Week in Science. This Week in Science. This Week in Science. 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 This Week in Science. This Week in Science. This Week in Science. 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 I've got one disclaimer, and it shouldn't be news, that what I say may not represent your views, but I've done the calculations and I've got a plan. If you listen to the science, you may just yet understand that we're not trying to threaten your philosophy. We're just trying to save the world from jeopardy. Jeopardy. And This Week in Science is coming your way. So everybody listen to everything we say, and if you use our method instead of rolling a die, we may rid the world of toxoplasma gondii. 'Cause it's This Week in Science. This Week in Science. This Week in Science. 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 This Week in Science. This Week in Science. This Week in Science. 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 I've got a laundry list of items I want to address. From stopping global hunger to dredging Loch Ness. I'm trying to promote more rational thought, and I'll try to answer any question you've got. But how can I ever see the changes I seek when I can only set up shop 1 hour a week? This Week in Science is coming your way. You better just listen to what we say, and if you've learned anything from the words that we've said, then please just remember it's all in your head. Cause it's This Week in Science. This Week in Science. This Week in Science. 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 This Week in Science. This Week in Science. This Week in Science. 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 This Week in 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 Science.
So, is this where I apologize for keeping everybody up so late?
This is at will podcasting, so
At will.
they can all leave. We can't.
know. We can't do the show.
But they can.
No. I'm sorry, Goldizator.
Sadie is so angry we're still awake.
Sadie's like, what are you doing awake?
Like,
This is when you go to
"Excuse
bed.
me, it's time to tuck me in because it's late. Her
It's
bedtime
late.
is normally 9 o'clock,
Ooh, except for Wednesdays.
except for Wednesdays.
Except for tonight. Yes.
Very needy. I'm petting her with my foot.
Oh, did you see the cool picture Gorov was talking about in, was it Europa, Titan, Enceladus? We have a wonderful moon, Gorov, but I do have to say, have you all seen the pictures of Enceladus? A really neat picture from this last week that makes it look like there's something hatching out of it. There it is. They used infrared to look at Enceladus, and this image is ridiculous. Oh, come on. Why do they have to make it so hard to look at? I'm going to find this here. Hold on. Nope. I just want a single image. It seriously looks like something is trying to claw its way out of the moon. But really, it's just heated liquid under the icy surface. So it's like something's like 3 big fingers going tearing out from the inside of Enceladus.
Dirt.
Enceladus is not a moon. That's no moon. It's an egg. It's an egg. Yes, South Pole picture, Carol Ann. Yep, you got it. It's so cool. I really, really, really like it. Can I make it? I can make it bigger in the picture. Brah. Yeah, but it's this was a Cassini instrument, the VIMS instrument that they put together. Yeah. Thought that was pretty cool. Thought it was pretty neat. It's late. I moved. What? Where did Justin go? He's not back. Oh, they did that's right. They did a Doctor Who episode about that. I also, yeah, it looks like the moon is bleeding a little. Random genre talk. It's so neat looking. Yeah, but to be able to, and so the South Pole of Enceladus is where the plumes of liquid water they've seen venting out, the geysers they've seen venting out from the surface of the moon. That's where they come from. So it's really, really interesting. You're tired. Sadie's tired. Oh, there's Jackson Fly.
You hear her?
Here's Jack.
She just went.
Yeah, we do know this already. The moon
gotta go
is,
to bed.
in case anybody's confused, the moon is just a giant space egg with a large space creature inside of it.
Yep.
That's common knowledge, I think, at this point.
Yep.
I mean, it's in reality, it's not that far. It's like it budded from the Earth, right? It's like a
Right.
budding event.
It did. That's right.
So,
It's not alive. It's alive.
what's happening here?
I don't know. I have green screen material.
Oh.
Ugh, much fun can be had with green screen material.
So
I don't-
much fun
so-
can be had by random people on the internet with green screen material, so you have to be careful.
Oh, be careful.
Well,
Random genre talk. We don't. So it's kind of like Schrodinger's tardigrades. They're alive as long as we don't know that they're dead. So
Yeah.
we can just imagine them alive on the moon. Was that Israeli tardigrades? Was that what they were?
Did they actually make it there? Was that right?
did.
They were on board and then got
It made it, but it crashed.
yeah.
So maybe not.
Maybe not. I think they were supposed to be, there was some discussion of genetically engineering them to be able to survive on the moon. I don't know if that.
What? They
Course.
already are.
No.
No, or in space. Something. There was
They already
some-
do. They can survive
Nobody
in
needs-
space.
Yeah, nobody
Yeah,
needs
there
to
was,
genetically engineer tardigrades. They're already indestructible and super
Uh,
survivable.
There was something about this. I don't recall the details.
They might have survived on their own. I'm not going all in.
They
for-
can survive. They can
No.
survive in space. So then, why would the moon be any different? It might be easier.
But yeah. It did. I think the question was whether or not they were in a desiccated form when the crash happened,
So
because that wasn't, I think, supposed
they
to.
were in a container of some sort. So
Right,
also
they're probably
that's the
they're
thing,
like in a
that
coffee
has-
can on the surface of the moon.
Yeah, they might still be stuck in the box. So there's also that.
Oh my goodness. All right. It is. What are the tardigrades going to eat?
I can
Each
on the
other?
moon. Yes, of course.
Each other.
The moon is made of cheese. Duh.
Uh,
That's right. Life finds a way. They could survive.
it does.
Mm,
Sounds familiar.
that would be so interesting. So interesting.
Oh, you're yawning. Do you want to say goodnight, Blair?
Good night, Blair.
You
Do you want to say good morning, Justin?
Good morning, Justin.
late.
Good night, Kiki.
Good night, everyone. Thank you for joining us. Sorry we're not going to do a long after show, but I think
We did
Good
a long
long
show.
tired. We did a long show. Faux show. So everyone have a wonderful week. Like I said, stay well and register to vote if you're not registered. And if you see that toilet fire, you're not alone. Everyone take care. It's our shared dissociative reality.